Hello and welcome. This is the Algebra 1-2 Spring Final Exam Video Review. And I will be covering the following problem types. Okay, anything involving sequences, arithmetic, geometric, etc. Word problems. Now, there won't be a very nice, big, wide variety, actually. In fact, the ones that I'm going to recap are actually kind of all the same from one another in terms of setting up and solving, but more explanation, I think, the more you'll get an understanding of it. Exponential functions, having to do mostly with the equation from a graph, or graph from an equation. Okay? Graphing inequalities, they'll all come in standard form, so you get to practice some other solving for y stuff too, as well as switching the inequality with that in the shading of it, and it'll be in a system, so you get to do two graphs in one. And finally, linear regression. So anything involving the statistics, interpreting slope and y-intercept, getting to see a scatter plot with a set of values, and being able to explain it. Now, there are some types of problems that will not appear in here, although they are talked about, as well as some topics that will not be covered. Big one that is missing, that's conspicuously absent, is anything involving quadratics. Okay, this will not be on this video. There is another video that was all from another packet, a solution guide that did cover a good plethora of problems involving quadratics, mostly from things like factoring them, distributing and expanding them, solving for them using either the zero product property when in factored form, or there's one or two completing the square problems as well, or quadratic formula, or even, all the different graphing types. Not too much that I have on graphing with this set of quadratics. I will hit you up with a bunch of different other videos that has that. But this is the big one that's missing from here that would otherwise be utilized in some other way. Trying to think of some other ones that would be, but this is the big missing chapter in this piece. Okay, so I do apologize for that. Just this packet did not have those because those were already uniquely done in another set. Now these will come in this order, and I'll kind of tell you once again how this is happening. This is coming from a packet, and this packet had a bunch of problems, and I'm going to say dozens, if not hundreds of different problems, right? I only circled up to, I think it was 28 problems. Okay. I'm going to say dozens of problems, not hundreds, but I'm going to circle 20. I circled 28 problems for you to try, and those are the problems that I'm going to do. And actually, the majority of them do come from sequences because there are a lot of different varieties of those. Then there are a few word problems, I think 5 of them. 4 or so exponential problems, 2 to graph, 2 to get the equation of. And I think 6 graphing inequality problems and only 2 linear regression problems, but they have parts A through E on them. So like I said, total of 28, I think, within here. Feel free to skip around as you need to for the types of problems that you know how to do or don't know how to do, etc. And like I said, there's a whole nother set for quadratics elsewhere, but I hope these serve as useful. What I'm going to do is spend the time kind of teaching them at the same time that I'm talking about the problem that I'm doing, and maybe I do multiple variations of the same problem type. So off we go. This video might take some time, but once again, this video is here for your sake only, where you can get some good studying measure in, and also even finish a couple problems here and there. And there are some bonus problems for you to try in that packet outside of the ones that I'm going to do. Okay. So this first one is on sequences. We are going to find the 3 terms in the sequence after the last one given. So in problem number 1 here, you have value number negative 13, value number 17, value number 47, and value number 77. Now in these problems here, I keep stressing the word value because that's exactly what they are. They are values at very specific positions. That's how sequences work. You have a position and a value at that position. What I'm going to do is split this up into a table of sorts. All right, these positions all have breaking parts, right? Because they're different positions. There's position number 1, position number 2, etc. And what we're going to find in a bit is 5, 6, and 7. Now I imagine that you already know how to find these because you are seeking the pattern here. And the pattern happens to be a common difference. A common difference between these values. There's something that's being added or subtracted that is continuously happening over and over and over. And it's good that you have at least 3 terms so you can say, oh, hey, look, the same thing happened again from the last time, which is exactly what you need. 4 definitely verifies that. If you just have 1, well, there are multiple ways to get from 17 to 47. I can multiply by 47 over 17, right? There are, so I don't want you to really try that. But it depends on the sequence type. So these are called arithmetic sequences. And in an arithmetic sequence, you do have that common difference. In this case, you say, what is 47 minus 17? Because that's what I'm adding here to get there. Oh, it looks like it's 30. What is 77 minus 47? Oh, it looks like that's what I'm adding to get there. Whatever this number minus 77 is also 30. So when I add 30 to this one, then I'll get the number, which is 107. Plus another 30 is 137. Plus another 30 is 167. Now you might have noticed that I didn't do this one right here, and there was no other reason other than to say I want you to get used to how differences work. It's the current, if you want to call this the current term, minus the previous term. So current term minus previous term, current term minus previous term. Now how do you do 17 minus negative 13? Well, exactly like that. So 17 minus, this should be a 13, negative 13, that's 17 plus 13. Guess what? That's still 30. So that still is a difference of 30. I didn't just do 17 minus 13, because the difference between 17 and negative 13 is not 4. Right? It is 30. They are 30 apart. So all of these are, and that's what you do, and that's how you fill those things in. Now let me talk a little bit more about sequences in the sense that I referred to position, number, and value at that position. And here's the notation we've kind of been using. Okay? Looks like this. Position number is n. The value of that position is t of n, the function of that term position. So if I wanted to find t of 1, that value would be negative 13. Or t of 5, that value would be 107. Now we start our sequences really at term number 1, but what a valuable number would be to try and find, especially when it comes to writing the equation, and we'll be getting those as well, is finding term number 0. Because what we want to do is we want to start writing equations in what's called explicit form. And in explicit form, you use the term position to describe what the term value is. And I'll explain that momentarily, but basically it's like a y equals mx plus b form. You use x to explain where your y is. You don't use a previous y value to explain it. So in other words, I can calculate 137 using the number 6, just like I can calculate 47 using the number 3. And there's a very specific way to do that, and the best way to do it, in my opinion, is to find a term number 0. This is equivalent to finding the y-intercept in an equation right here, because as you can see, we started at n equals 1, just like at x equals 1. That's not the y-intercept. The y-intercept is x equals 0. So what is the value of t of n when n equals 0? Well, it's 30 less than the time before, right? What number do you add 32 to get negative 13? That number is negative 43. So this stuff is going to be very important for a future problem when it comes to answering it. I will answer this one for you as far as what the equation is. If this is like y equals mx plus b, okay, your m, your slope, is how much you're increasing by, the common difference. That's going to be 30. 30n represents how many times you add 30 from where? Well, from a good starting value, such as negative 43. Okay. Here's an equation in explicit form that describes this right here. You might say, oh yeah, we're adding 30 each time. Well, you're adding 30 from the previous value, but how many times are you adding 30 from some base value like negative 43? So the answer is, in term number 1, you add 30 once. In term number 2, you add 30 twice. In term number 3, you add 30 3 times. As you can imagine, this keeps going. In term number 90, you add 30 90 times. And that's where this 30n works here. Term number 90 says 30 times 90. That's 30 plus 30, 90 times. Starting from negative 43, that can help get you there. Now, once again, those sequences do start at the first term. This is a little hidden, invisible one that you don't see from there. So now that I just talked about it, hopefully you start to kind of get that concept as I continue on for our next problem. But these are the next 3 terms in the sequence: 107, 137, 167. Number 5, and as you can tell, we skipped 2, 3, and 4. Those were not problems that I circled at the time, so feel free to try and do those ones if you can. Okay, find the explicit formula. So I just did that last time, and it looked like so. To find the value at term n, you take your common difference, you multiply it n times, basically the same as the position number, and you add that from a base value of term number 0. Now term number 0, once again, is the term before term number 1, which you don't see here. So I'm going to do this table one more time for you. I can't really do straight lines. Yeah. Here's 0, we don't know yet. 1, 2, 3, 4. And these values that we have are -3, 3, 9, and 15. So once again, the idea is to first find that common difference, because how do you find term 0 other than to find out what number we had to add or subtract from term 0 to get to term number 1? Well, looks like it's 6. 9 minus 3, 15 minus 9, and also, of course, 3 minus -3. So if we're going to add 6 from term 0 to get -3, term 0 must have been -3 minus 6. That number is -9. So term 0, -9, is a good base point. And let me re-explain this t of n business one more time. This time, I will actually flip the order. I'm going to have term 0 written first and then d of n written next. To find the value at position n, let's start from -9 and then let's add our common difference of 6 n times. I think this order is a better telling explanation of what it is you're actually doing. Once again, we technically start at term number 1. Term number 1, if we use -9 to start from, we're going to add 6 once. That number is -9 plus 6, that's -3, as you can tell here. Term number 2, starting from -9, we are going to count how many times we add 6. This time it will be twice. -9 plus 12 is, help me out, 3. Term number, and this keeps going, so I'm going to find a larger one for you, like term number 100. Term number 100, starting from the number -9, we are going to add 6 100 times. That's -9 plus 600. That's 591. So you can see how quickly we can come up with these, and it's actually kind of a nice process because it doesn't depend on any term before it, and furthermore, you can find any of them on the fly. The explanation of it kind of gets a little confusing for some people, so just do the best you can with it. But keep in mind, this is an arithmetic sequence with a common difference, so this is just like y equals mx plus b form. In this case, b is -9, your y-intercept, and that's why we write it in this format, so it's very close to looking like y equals 6x minus 9. It does the exact same thing, too, regarding a graph. The real difference, though, is that terms are integers only, and really they're the whole numbers starting only at 1. The counting numbers, 1, 2, 3, 4. So if we saw this on a graph, you'd be not looking at a line that starts from -9 and goes up sharply, like up 6 over 1. What you would see is a graph where it starts at -3, at 1, and then at 2 it jumps up to 3, and 3 like that. This is how a sequence graph works because these are just position values. There is no term number 1.5 technically in a sequence, and that's really the biggest difference that I can mark here. Okay, find the recursive formula. So this is the one that I think that most people are able to better describe, but possibly not write out, only because the notation is so funky. Okay, so now that you've understood that we're at term number 1, 2, 3, and 4, let me first begin writing out here that term number 1 is -18. Because the entire thing behind recursive formula, the word recursion means an iterated like loop. You're applying something to the previous something that you had. Okay. In this case here, if I ask you to describe what this pattern is doing, most people would say, after they really notice these ones, you're adding 9. And they're not wrong. You are adding 9. But that's not enough of an explanation. You have to make sure that you have a reference value to which you're adding 9 from. Because if you just told me, like, Mr. Robinson, could you add 9? I'll go, sure. And then you stop me and you say, no, not from 2 or not from -7 or whatever it is. You say, no, do it from -18. And I go, oh, okay. So from -18, let's add 9. Then you get your thing going, and 18, etc. So you have to refer to where it is you want to start from. So here's how the notation looks. Okay, to find the value of your next term, and remember, term is all about the position you're at. Here's position n. What's the term after position n? It's position n plus 1. To find the value of position n plus 1, we are going to take the value of position n and we are going to add our common difference. Okay, so here's what the recursion formula looks like. So to do this one here, it's going to look the exact same, only we're going to include our common difference of 9. There you go. And also, we want to make mention of where we are starting from. There it is. Now, I know that looks really funny to you because there are probably more letters here than there are numbers. And the function notation, kind of throws us off a little bit. But it does not take away from what all of this means. To find the value at the term after your current term, you take your current term and you add 9 to it. So, and it's starting from t of 1. So what's good about this one is, first of all, it's very easy to describe out loud in person. And second of all, it's very easy to find the next value after you already know the value before it. So if I knew that term number 23 was something, by the way, I don't know what it is off the top of my head, so I'll make one up. If term number 23 was, 207, okay, well, to find term number 24, you take 207 and you add 9 to it. That's 216. So that was pretty simple, right? The problem is, if you didn't know what term number 23 was, term number 24 is going to be kind of hard to find. Why? Because you have to add 9 24 times. Now, that's sounding a lot like explicit formula. Yes, it is. But as far as recursion, if it said, write out the steps, find term number 5 by using term number 4, find term number 6 by using term number 5. All right, well, that's going to take some time. But that doesn't make this one a flawed system at all. Like I said, most people kind of prefer this kind of pattern description. Most people do not, and I repeat, do not explain a sequence by what term position you're at least not out loud. You don't say, oh, look, to find the fourth term, you're going to have to multiply, your common difference by 4, and we're going to start that from term 0. No, you're going to say, oh, let's add 9, and I have to add in a little bit more. Starting from negative 18, let's keep adding 9 over and over. No problem. Two different ways, both have their own benefits. We're going to keep using them down the line. Number 9, now we are given the explicit formula, and actually before you do anything with this, or before we solve the problem, I'm going to let you know that if you're looking at an a sub n like that, that is the exact same thing as t of n. It's just a different notation. I'm not sure why it's considered or being used. Just keep that in mind. These are both the same thing. So as I do this problem, I'm going to rewrite it so it looks like this. That's an equal sign. 12 minus 30n. And I like how they did not use this as mx plus b, because I can keep talking about how this common difference works with the explicit formula. So given the explicit formula, for an arithmetic sequence, find the first 5 terms. So we are going to write out what term number 1, 2, 3, 4, and 5 are. Okay. First of all, term number 1 is not 12. This is where we are starting from as far as explaining this stuff, but term number 1 is at position n equals 1. So to find t of 1, what I'm going to do is take 12 and subtract 30 only one time. So that's 12 minus 30, which is negative 18. That is term number 1. I'm going to write it right up there. Negative. Term number 2 starts from that base value of 12, and we're going to subtract 30 twice. So 12 minus 30 was negative 18. 12 minus another 30, which is 12 minus 60, is going to be negative 48. So we get negative 48 there. So you can kind of see how this is going. And once again, you don't have to kind of use the explicit formula to make things happen. You have to use it to describe what it is you're doing so you can solve what it is you're going for. I mean, you can solve any problem however you'd like. So if I kept going here, honestly, I would not be plugging all these in just like this. I know that the next one is going to be 30 less than this one. But keep in mind, we started from term 0. And term 0 is not a part of the official list. That's why I'm not writing 12 right here. Negative 30 is your common difference, which means between each value is a 30, but going in the negative direction here. And we continue on. Hang on. The next one is 12 minus 90, which is 30 less than 12 minus 60, so that's going to be negative 78, and this keeps going to negative 108 and negative 138. Assuming I did my non-calculator math correct, that's where we're going with that. So there are the first 5 terms, and this goes on forever. Okay. Now remember, this is term 1, not the 12. However, the 12 was still very useful. Okay. Given the recursive formula for an arithmetic sequence, find the first 5 terms. Okay, so this is, once again, probably maybe an easier kind of way to do things, because this is probably how you go through the description stuff. First of all, I'm going to rewrite this so you just have a clue at what the heck this means compared to that of what we've done before. Now look, you can use a sub n as well. I'm not quite certain why one might be used over the other. I've never truly done that for myself, but there's function notation and there's subscript notation. Both of them will be used in your life for more than just math. Physics, well, physics is math, but in that set. So, here we go. T of n plus 1 equals t of n minus 2, and t of 1 equals 36. What does all that mean? First of all, your first term is 36. Second of all, to find the value of your next term, you're going to take the value of the term that you're at and subtract 2 from it. So as far as the first 5 terms, to make sure this makes sense, your first term is 36. So I already have my first term. Second term, as you can tell from this equation here, from this recursive formula, to find the value of n plus 1, I'm going to take the value at term n, and I'm going to subtract 2. Well, to find t of 2, t of 1 is 36. So I'm going to do 36 minus 2. So t of 2 is 34. So this one here is 34. And you can tell, once again, that, well, you know, if you write all this stuff out, you're going to probably lose your head. All right, let me do one more to really make you lose your head here. To find the value of the third term, you take the value of the term before it, and you subtract 2. Well, the value of the term before it, we have now discovered, was 34, and 34 minus 2 would be the third term, which is 32. So this one here is 32. And once again, the reason why I'm making mention of that is so you get comfortable with this, and so you can explain out loud exactly what it is you're doing. These formulas aren't so bad when you know exactly what it's describing. And that's what it is describing. So what are the next 2 terms? Subtract 2 from 32, subtract 2 from 30. Those are the first 5 terms, and it keeps going on and on. If you want a term 0 to reference, especially when it comes to writing an explicit equation, it would be 38. Furthermore, and actually I'm going to do this with the previous problem as well, if you want to write an explicit formula for this right now with me, let's go ahead. To find the value at position n, starting from 38, we are going to subtract 2 n times. Okay, that's the explicit form for this. Now, if I were to go back and do the previous problem, let me write a recursive formula for this one as well to get you comfortable with that. To find the value, to find the value of the next term here, you take the term before it and you subtract 30, the common difference, and your first term that you are starting from here is negative 18. Once again, the base term 0 value of 12 was not our starting term in our sequence. So at least you're getting comfortability and a tie-in on how one goes with the next. Okay, that was arithmetic sequences. Now we're going to jump in what are called geometric sequences. And with this kind of comes a good old set of different things here. These aren't linear anymore. Now these are exponential. So as exponential functions will come later, this is a good heads-up start to how they look. Okay. If you first look and you decide to determine whether this is geometric or arithmetic, remember that arithmetic sequences have a common difference. What's the difference between negative 2 and 8? Well, I would add 10 to get there. How about from 8 to negative 32? Well, that's minus 40. Negative 32 to 128, that's 160. And you're going, what the? What's going on here? And you find out this isn't a common difference. In fact, they tell us it's common ratio. So common ratio, by that, ratio means that whatever you're multiplying by from here to here, you're doing the same thing from here to here. It's growing at that same rate. Now this one from negative 2 to 8, how do you find out? I'm not asking what it is. I know that we all know, in a way, what you have to multiply negative 2 by to get to 8. I'm asking, how do you figure out what it is? Because what if I asked you later, what do you do from negative 32 to 128, and you didn't know these before it? Well, that's going to take you a second longer to figure it out. What we're going to do is divide negative 2 from 8. 8 divided by negative 2 will get us our common ratio. And we need to see if negative 32 divided by 8 will give us the same thing, and 128 divided by negative 32 as well. All of these, written in fraction form, would look like that, probably a little better. Now notice how this also alternates sign, which means we must be multiplying by a negative number each time. 8 divided by negative 2, that's negative 4. Negative 32 divided by 8, that's negative 4. 128 divided by negative 32, let's trust it, negative 4, of course. So your common ratio R is negative 4. And as far as common ratio goes, it's describing what you're multiplying by from one term to get to the next. As you can tell, we'll be using this for recursion pretty soon. If you wanted to find the next term, you multiply by negative 4. So that'll be negative, to be honest, I don't know. Negative 4, let's say, negative 512? I should know that. I think it's negative 512. Number 19, find the common ratio here. What number are we multiplying by to get from one to the next? First of all, if I describe this pattern and I said, there's one thing you're doing from one thing to the next, what is it? You might find out that it looks like a little bit of a division thing. You might say, divide by 3, and you would not be wrong. Yes, we are dividing by 3 to get from one to the next to the next. Problem is, when applying a ratio, some sort of scalar factor, we really call it multiplication. So when you're multiplying, the question is, what number are you multiplying by to get here? I know we're dividing by 3, but what is that equivalent to in terms of multiplying? Well, just do the exact same thing as you did before. And I know fractions might be a little scary and strange and different, but let's work with it. How did we do it here before? What do you multiply from negative 3 to get to negative 1? You take negative 1 and you divide by negative 3. So here we go. Negative 1 divided by negative 3. That'll be equal to whatever negative 1/3 divided by negative 1 is. That'll be equal to whatever negative 1/9 divided by negative 1/3 is. Now you can use a calculator for any of these things to work with them, but keep in mind how much the parentheses matter. They matter a whole lot. All of these happen to reduce to one value here as a fraction. A negative divided by a negative is equal to a positive. This is 1/3, all of these. You are taking 1/3 of your previous number, which, yes, that's dividing by 3, but you are multiplying these numbers by 1/3 to make it happen. Your common ratio here is 1/3. And keep in mind, all these numbers are negative. They will remain negative now and forevermore, and they will arrive at the asymptote of 0, right? This will converge at that point. It will never quite exactly reach it, but it'll keep getting small enough that it might as well be 0. And I hope we get some talks about that over time in exponential functions. So from here, if you want to take 1/3 of negative 1/9, you multiply negative 1/9 by 1/3, and that becomes negative 1/27. And then the next one is negative 1/81, and that keeps going as such. These numbers are getting smaller because the denominator is getting larger as the numerator stays the same. They're not getting smaller in value, though, just in absolute value. Notice these numbers are getting closer to 0 from the negative side, so they're actually technically getting larger, which is actually interesting, but not something you needed to know. Find the 3 terms in the sequence after the last one given. So the last one given is 27. We have to figure out what happens next. So, as I explained with the previous one with arithmetic sequences, to find that, you have to first try and describe this pattern in some way. And remember, this is a geometric sequence, which means there is a common ratio. What are we multiplying by? As you can tell, it's 3. 3 over 1, 9 over 3, 27 over 9. These are all 3. As we multiply by 3, let's multiply 27 by 3, and we get 81. Multiply 81 by 3, and we get 243. Multiply 243 by 3, and we get 729. That's all you have to do for this problem, but now, because I assume the explicit and recursive formula comes next here, I want to start talking about those a little bit as well, because this is where things get a little scary for people. Before we did linear equations, okay? Now we're looking at exponential equations. Linear equations describe how many times you add a number over and over. Exponential equations, like geometric sequences, explain how many times you multiply a number over and over and over. So what's going to be important here is, once again, treat these as sequences with n and t of n. Okay? Now, value, term number 1 is still 1, and 2 is 3, and 3 is 9, and 4 is 27, and this keeps going 5, 6, 7. Okay? You might ask yourself to have a term number 0. I'll show you why sometimes it's not very good to have a term number 0 in these cases. And there are actually two options that you have for this. Either find term number 0, which means whatever number you multiply by 3 to get 1, figure out what that number is by dividing by 3. What number is that? Well, it's 1/3. A fraction. See, we don't like those. I mean, I'm fine with them, but I'm sure you're not. So if you want your term number 0 to be 1/3, knock yourself out. Completely valid. And furthermore, it's probably important that you understand what these two different explicit forms of equations can look like. So let me kind of explain to you how this will work two different ways. In explicit form, if you want to find the value at position n, where does position n come into play? Well, in arithmetic sequences, it was how many times you added your common difference. In geometric sequences, it's how many times you multiply your common ratio. So to go from term number 0 to term number 1, we've multiplied by 3 just once. To get to term number 2, we multiply by 3 twice. Term number 5, multiply by 3 5 times. So the n in this case is going to appear in the exponent. This exponent, this little n up here, will describe how many times we multiply this number 3. 3 to the n says we multiply 3 by itself n times, starting from some value. In this case, our starting value would have been 1/3. This is, right here, one of the formulas for explicit form for a geometric sequence. And it looks as follows. T of n equals your term 0 multiplied by your common ratio raised to the n power. Some people prefer this. The reason why some people don't like it is because a lot of times your term 0 is a fraction. They start this with integers in mind, but they don't assume that the one before it can also divide by your common ratio. So what some people do, they don't like the fraction, they say, let's start at term 1 instead. So they say, let's start at 1. Now I'm going to multiply by 3 a certain number of times. The question is, for term number n, do we multiply by n times? Well, let's take a look. If we start from 1, if we want to find position term 2, how many times do we have to multiply by 3? Once. For term 2, we're multiplying by it once. For term 3, how many times do we multiply by it? 1, 2. Twice. Term 3 is twice. Term 4 is 3 times. Term 7, 1, 2, 3, 4, 5, 6 times. So it's one less time than the term number to which you're referring to. So if we are referring to term number n, we have to multiply by 3 one less time than that. This is where people start to get a little bit lost with that notation. Starting from term number 1, you multiply by r one less time than you would have before. Keep in mind, you can do this for arithmetic sequences as well, just it's not as advised to do it because we like to use mx plus b form, and furthermore, our term 0 normally isn't any more estranged than term number 1. If it was an integer before, it's probably an integer thereafter. This case, this happens a lot where it's not like this. Now, they didn't ask you to do this for this problem. You only had to find the first 3 terms. There they are. I'm giving you an example of what explicit form looks like because we're about to jump into that. And then after that, we'll do some recursive ones. 2 different ways to express the exact same thing. Remember, these are the exact same equation. As you can tell, this one was multiplied by 3 one more time than this one. So this is why we have to multiply by 3 one more time here, then in this one. Get it? All right, find the explicit formula. So now we're at that point. And actually, this one will be a very great term number 0. I'll show you why in a moment. To find out what you're multiplying from one to the next, it looks like they're sure using 3 a lot. Find out what you're multiplying from one to the next. You divide one from the previous one. Negative 9 divided by 3 is negative 3. 27 divided by negative 9 is negative 3. This is what gets you to confirm. This isn't x minus 3, by the way. This is times negative 3. Times negative 3, once again right here. This confirms that it's a geometric sequence, and it confirms that it has a common ratio by dividing one from the previous one. So your common ratio is negative 3. Your term number 1, if you'd like to use it, is 3. Your term number 0 would be negative 3 times less than your term number 1. So what do you multiply negative 3 from to get 3? That number was negative 1. 3 divided by negative 3. So your term number 0 is negative 1, not a fraction. So not bad. I'll still write both forms for you here. t of n using term 0. Term 0 starting from -1, and I'm going to multiply by -3 the same number of times as the position number that I'm at. Remember, term 1, I'm going to multiply by -3 once. Term 2, I'm going to multiply by -3 twice. 3 times, 4 times, 1,000 times, and that never changes. So n represents the same number of times that you multiply -3 to find the value at term n. The alternate way to write this one is to start from term number 1, which is 3, and we're going to multiply by your position value, we're going to multiply by -3 one less time than the position value to which you are referring. If I wanted to find term number 100, I would start from term 1, and I'd have to multiply by -3 99 times. That's 100 minus 1. So either or is valid here. Both of them work. That's why I'm giving you both of them. And I will continue to do that for each and every problem that we have this with. Now, before I jump on to the next one, because I believe the next one's recursive, let me keep in mind one thing that this looks like, especially this first one here, which is why I'm actually emphasizing it, regardless whether it's fractions. This looks like y equals ab to the x form. This is exponential functions right here. Starting value, growth factor, and how many times you grow it by. Okay, so I'm keeping this in this form every so often, so you're just familiarizing yourself with it for when I get to exponential functions. And let me also recap one last time, because I think I only talked about this for the very, very first problem here. These are actually points on a graph. Okay, there's a point here that's 0, -1. There's another point here that's 1, 3. See, these are like x. Remember, n and t of n are like x and y. They very much are. These are just points on a graph. And I want to keep that in mind because tables work that exact same way regardless. And we can also graph these too. At some point, I will show you kind of what a graph looks like in this case. All right, find the recursive formula. Now, this one increases very sharply in the negative direction. Either way, you're still multiplying by something. Let's figure out what it is. From -2 to -4, -4 to -8. Yeah, you're doubling them. You're multiplying by +2. That's your common ratio. R is +2. Are you positive? Yep. You guys aren't. Times 2, times 2, times 2. You can imagine what the next ones are. Yeah. Okay. So let's figure out how you describe this thing. Well, we just did. You multiply by 2 from your previous value. Now remember how recursive formula works though. You need to say where you're starting from. We're only starting from t of 1. We really are. As far as our list goes, our first term is -2. From there, let's keep doubling it. Okay. So that'll be an important part of this formula here. And for the next part, very straightforward. To find the value of the next term, you take the value of the term before it, and you double it. That's all. And then, of course, this little footnote goes in thereafter. So I know people don't really like the look of what this looks like because, once again, the parentheses, the letters, a lot of things looking like this. Even t's look like pluses. Maybe that's why they don't like using t's. Sometimes they instead use a. But that is your description of the problem. To find the value of the next term, you take the value of the term before it and you double it. And this continues on and on. And I do believe that the next set of problems will look like that. So I'm going to do like what I did last time. I'm also going to write in explicit form for this problem here. And I'm going to write a recursive form for the problem right before this one. Explicit form, there are 2 different equations we can do. Remember that. Let's do one using term number 1, -2. Starting from -2, you count how many times you multiply to get to the terms thereafter. For term number 2, you multiply once. Term number 3, you multiply twice. Term number 4, you multiply 3 times. Term number n, you multiply 1 less time than n minus 1. And that is one of the forms. The second form you can do is with term number 0. And what's great about this term number 0, once again, divide by 2, that's -1. It ain't a bad number. It's not a fraction. And there's nothing really wrong with a fraction. Maybe you just have trouble computing the fraction, right? But writing a fraction isn't too bad. That's all you got to do. One or the other, they are the exact same equation in explicit form. Going back to the problem before this, recursive form for this one would have looked as follows. To find the value of the next term, you take the value of the term before it, and you multiply it by -3. we start this from term number 1, which is 3. By the way, you do not have to mention what term number 1 is. You have to mention what some term value is. I could have said t of 4 is negative 81, right? They might give you that on a test. They might say, write the first 5 terms of this thing and using the recursive sequence, and they give you term number 4. All right, well, that's fine. To find term number 3, you divide by negative 3, and you do it again for negative 2 and again for negative 1. So just term number 1 is the best base value to consider what it is you're talking about. Given the explicit formula for a geometric sequence, find the common ratio in the first 5 terms. No problem. First things first, a sub n. Maybe you're not familiar with it. Change it to t of n. Either or. Either way is fine. Now, let's look at this one. Take a look. They use explicit form, and in this one, they use the n minus 1, which means this is t of 1. Okay? If they're using n minus 1, this is term number 1, not term number 0, because they're multiplying by n one less time than they need to. So this one actually looks like that. Okay? So the first 5 terms, your first term is negative 3. That is the first one. The second one, term number 2, oh, and if you don't believe me, here, let's do this. T of 1 equals negative 3, and here's actually what you can just exercise anyway. You might as well plug them in. If n is 1, substitute 1 for n, 1 minus 1 power. So that's negative 3 times negative 4 to the 0 power. Negative 4 to the 0 power, such as any non-zero number to the 0 power, is 1. What is negative 3 times 1? Well, that is negative 3. So that is term number 1, as I said before. Term number 2 is taking negative 3 and multiplying by negative 4 one time less than the number 2, which is 1. Negative 4 to the first power, which means we're multiplying by negative 4 only once, which is positive 12. The third one here, and after I do this one, I really do hope you pick up the pattern of what's happening each and every time. Find term 3, starting from negative 3, the first term here. We're going to multiply by negative 4 twice because it's 3 minus 1. So negative 4 squared is negative 4 times negative 4. That's is positive 16. And negative 3 times 16 is negative 48. So term number 3 is negative 48. So a couple things that are going on here. First of all, we're multiplying by negative 4 each time. Second of all, as we multiply by a negative number, the sign changes each time. So you probably get to the calculator hereafter. I think this number is positive 192. And after that is negative something. Let's see, negative 400 was negative 36. 768. I'm going to actually use a calculator for that and not trust that I'm right for any particular reason. 192 times negative 4 is negative 768. Okay, there we go. That's the first 5 terms. But notice how I calculated them. Okay. Systematically, I'm substituting n right here. That's as straightforward as it gets. But then hopefully you catch on to the fact that saying, oh, look, I'm just multiplying by negative 4. Yeah, man, that's what the common ratio is talking about. Now, term number 1 was probably a good one to test in case you're like, is this term number 1 or term number 0? After you practice this one, and by the way, what would have this looked like if we did with term number 0 instead? Well, what is term number 0, guys? Do you know? Here's term number 1. Term number 0, we had to multiply by negative 4 to get to negative 3. So negative 3 divided by negative 4 would have been term number 0. That's positive 3 over 4. Okay, so we could have written this equation like this. Negative 4 to the n power. This is the exact same thing as this one here. And you notice why I keep re-emphasizing this, because I feel like it's an item that could be lost if it's not stated over and over again. So I won't stop talking about it as long as we're talking about sequences. Unfortunately, this might be the last sequence problem. Yep. So let me dive into something here for a second, if I can, just because we're done with sequences here on out. Let's use another problem. Like, I'm going to use this problem right here, and let's find a bigger number. Let's find t of 100. Now, first of all, I would not do that unless I had an explicit equation. which of course I'd have to create on my own. But I wouldn't use the recursive formula, do this 100 times, and figure out what it is. No, I'd use one of these two. They're both the same thing. Trust that that's true. T of 100, let's use the top one, equals negative 2 times 2 to the 100 minus 1 power, which is negative 2 times 2 to the 99 power. Honestly, I shouldn't have actually done this, because I don't think if I type 2 to the 99 power in my calculator, that's going to give me anything that'll work. Yeah, it's just going to give me a massive number. So you're going to take this massive number. This is 2 times 2, 99 times. That's huge. Remember, 2 to the 10th power is 1,024. Right. Once you get to 2 to the 30th power, you're already in like the, oh gosh, you're in the tens or hundreds of millions. All right, that's the, boy, you're going a long way. And then you multiply by negative 2. All I know is it's a negative number. All of these are negative. So that was a dumb example for me to do. But also on this graph, remember how I was mentioning how these are also coordinate points? I'd like for you to at least see what this looks like on a graph with or without the actual curve attached to it. Because in a sequence, curves don't actually exist with this. So there are some points here. So if I drew a really quick graph, like, let's use black. Really quick looking graph before we actually get to the graphing problems after our word problems here. Here's some points, 0, 1, 2, 3, and 4. Remember, these went negative. First, there's a point called 0, negative 1. Pretend like it's about right there. Let's get better with this. This is negative, how about this is negative 10, so this is negative 5. So maybe that's about negative 1 right there. There we go. So we can fit everything. Then there's the point 1, negative 2, 2, negative 4, 3, negative 8, and 4, negative 16. Now, at first you might have thought this was linear, but as you can tell, this increasingly sharpens more and more downward. If I actually connected something with it, it would be a curve. It's not going to be a very good looking curve, sorry about this. But it never goes straight, not only for my drawing, because it does that, and it continues that way forever. Now, that's going to be more for the curves that we do, not for sequences. This is the sequence itself. This is the representation of continuous motion. And it continues to go down that pattern. It gets sharper and sharper as we go. 5 is negative 32. 6 is negative 64. So you can see it doesn't have a common difference. It has a common ratio. We are doubling our previous value, down and down. And we'll talk about what goes this way as well, how it converges to the point 0. All right, that's as much talking about this as I want to do. Let's go on to word problems here. Number 1, Elisa's school is selling tickets to a spring musical. On the first day of ticket sales, the school sold 18 senior citizen tickets and 5 child tickets for a total of $176. The school took in $302 on the second day by selling 36 senior citizen tickets and 5 child tickets. I don't know, that seems like not a lot of people. What is the price each of 1 senior citizen and 1 child ticket? Now, this is multiple choice. You could do some guess and check. I'm not going to. I'm going to actually set this thing up. I will talk about what setting this thing up looks like each and every time. Super, super duper important. And actually for this, I'm going to be defining variables, and I'm going to always be using X and Y. I know sometimes I'll say, hey, let's do S and C for senior citizen and child. Problem is, S looks like a 5. I don't want to be making things, you know. I want you to be used to X and Y because that's what you'll be doing for most systems of equations. So I'm going to define 2 variables, X and Y. X will represent the unknown of one of my set of values. There's missing, we don't know how many senior citizen tickets were sold. We know how many were sold. See, that's the problem. If you put senior citizen ticket, X is senior citizen tickets. Okay, the problem with that is, what does that mean? Does that mean the price of it? Does that mean the date that it was sold? Does that mean how many there are? It's cost. This one is cost. Our cost appears to be in dollars. Okay. There's nothing more important in these word problems, if not for yourself, or if not for the person who's grading it or whatever. I was going to put child citizen. How about child ticket cost? This is also super helpful for you. I'm going to show you why here in a second. There's why. I'm going to show you the reason for that in a second. we are going to create a system of equations. Basically, we are going to describe the 18 senior citizen tickets that were sold and the five child tickets that were sold for $176. We will also describe in another equation the next day of stuff using $302 by selling 36 senior citizen tickets and 5 child tickets. Look, if we only had one of these equations, if I told you guys, hey, I sold 18 senior citizen tickets and 5 child tickets for $176, how much did each cost? There is more than one answer. Okay, I'm telling you right now there's more than one answer. Take a look at this. What if I said senior citizen tickets were $2? How much did I make out of these 18 tickets? 18 times 2. Now there's a reason behind why I'm doing this as well. 18 times 2 is 36. Do you know how many child tickets I would have had to sell? Well, $140 worth, which would give me 28, I think. So if I sold 28 of those, that would take the 5 child tickets multiplied by 28. Sorry, I sold 5 of them. They costed $28 each, and that's $140. Okay, senior citizen tickets cost $2. Child tickets cost $28. Now, that sounds unreasonable to begin with, but that's not wrong. That does answer that. But there's more than one answer than just that. There's another set that's one of these 4 answers here. As you can tell, 2 and 28 is not on here, which means this one also worked. Why does another one work? Why are they asking me a question where there's more than one answer? Well, there's not more than one answer because this was only one part of the explanation. There's also a second explanation for a different day with different numbers. Because of this explanation here, there's only one set that makes both of these true, and we're going to figure that out. Now, I mentioned doing this part right here. And what I was talking about here was how much money you made by selling a certain number of tickets at a certain price. Okay, well, what did I say this was, 28? This is going to be important for my equation. I'm going to create 2 different equations that represent how much I made on 2 different days. On one day, I made, well, not me, Elisa. On one day, Elisa made $176. On the other day, Elisa made $302. Now, she did that by selling a certain number of senior citizen child tickets. We know how much they are. We sold 18 senior citizen tickets on this day. We sold 5 child tickets on this day. If we include the cost here, then we can get how much we made. So, 18 senior citizen tickets for blank dollars, for X dollars per senior citizen ticket will give you how much you sold, how much money you got selling senior citizen tickets. If I take 18 times 2, that's $36. That's $2 per ticket. 18 times $5 per ticket would be $90. 18 times X dollars per ticket would be 18X dollars. And I hope that that makes sense with what I'm talking about there. This term represents how much money I made selling senior citizen tickets. This number right here, like 5 times 28, I could have done 5 times 2. Whatever I set the price as, if I sold 5 child tickets, I'm going to take that price and multiply by the cost for each ticket. So this represents how much money I made selling child tickets here. And when I sold that, I equaled 176. My next set of equation, or my next expression, set of terms here, would be I sold 36 senior citizen tickets for X dollars each. So I make 36 times X amounts of money through senior citizen tickets, plus the 5 child tickets. Once again, this is going to be 5 again, and this is what I was mentioning. These setup problems might be a little hard. Solving them is actually going to be the easier part because I think one's going to line up with the other every single time. I wish it weren't so. I wish it made it more challenging. I wish I made it more challenging, but I didn't. Sorry about that. But here's the setup for this, and now we want to solve. Okay, how do we solve? Well, we are going to use something called the elimination method, and I think I'm going to do it each time unless I feel like there's something I can really do with substitution method. I'm going to solve for x and y by eliminating one of my variables. In this case, I'm going to try and eliminate y. Now to do this, and this is the best thing I can do for a system of equations that's going to explain it the best, I need to multiply one of my equations by some value, and when I have multiplied by that value, it will have affected the other one. So I'll do this 2 different times. How about that? That'll be helpful for you guys. If I multiply all this by -1, that makes all of these numbers negative. what that allows me to do, and I'm not going to explain why I can add down the list. I know I've done that before, so I'm going to refrain from that for the sake of time. When I go down here, as long as these things are lined up and on the same side of the equation, I can do the subtraction. What this allows me to do is cancel 5y and negative 5y. Whoops. 5y negative 5y is 0. So these cancel out like that. So 18x plus 0 equals whatever 302 minus 176 is. And that is, I think, 126. All right, so x is 126 divided by 18. I'm actually thinking about it. 5, 6, 7, I think. X is 7. Now x equals 7. That's great. Da-da-da. Are we done? Yay. No. We didn't answer the question yet. We got part of it, part of the answer. And furthermore, I want to know what this actually means, what this describes. All right. Well, this describes the cost of each senior citizen ticket. If you remember, this is part of the reason why we define the variables. X represents something. If you define what it stands for, that'll be perfect. Especially because it's multiple choice. How the heck are we going to do this? Unless, and look, if x equaled 7, you didn't know which one x was for, you might circle A or D. Because A here is this one, D here is this one. They both have 7. What's actually interesting about this is actually I already now know the answer. It's going to be A because none of these also have 7 with it. But I don't want to stop with this problem for the sake of helping you on what we're going to do for the rest of this problem. X equals 7. That's awesome. Okay, senior citizen tickets cost $7. So what I can do now is go into either equation. Any of these original ones are the preferred ones really to use. Substitute 7 for x in either one of these equations, and then you can solve for y. Now keep in mind, I'm going to do this part twice as well. I'm going to do a lot of this for you. It's going to be nice, good help. 18 times 7 plus 5y equals 176. 18 times 7, as we know, is 126. We just did that before. 126 plus 5y equals 176. 5y equals 50. And y equals 10. Each child ticket is $10. Now, if you were doing this as a system of equations, just so you're aware, your final answer should be a coordinate pair like that. But we're not doing this really as a graph. We're actually answering a question about senior citizen tickets and child tickets. And as you can tell, 7 and 10 ended up being the answers there. Ways to double check. You can plug in 10 and 7 into both equations and make sure it works. I'm just going to go ahead and do this a second time with the other equation, substituting 7 in for x and making sure that I still get the same thing. Because again, it needs to work for both, right? I can find different things like this one right here. I can find different ones that'll work for just one equation or just the other one. I need it to work for both days. I need to see what this total cost was. Okay. Now, I think if you're a Lisa, I think you should know how much money you're making off this stuff, right? But I don't know. Poor Elisa here. We're ragging on her. Now notice, as we subtract 252, we're back where we were before. 5y equals 50, y equals 10. So you're still getting 10 for the child ticket cost regardless of what you do. I used both equations, this one and this one over here, using different colors here. And I still solved for it. Okay, now what I'm going to do is erase all this work. And you're like, why? Because I want to do elimination method at least one more way, at least as long as I have a problem that's set up for perfect multiplication to eliminate the other variable. So I'm going to go ahead and erase all of that work except for the 2 equations that I originally had set up and give you one more way to do this so you're getting a little more familiar with how elimination method is processed. Now remember, these are larger numbers, but they're set up for probably very limited fraction work. So these are probably easier problems to do. However, we had to do the setup. Okay, this time I'm going to take this top equation and I'm going to multiply instead by -2. The reason for that is because I can eliminate my x's by getting this to now instead say -36. See how these now line up and these will cancel out? What happens here is 5y gets multiplied by -2 as well. That becomes -10y. And 176 gets multiplied by -2, and that becomes -352, I think. So all of these got multiplied by -2, and now when I add down this list here, these cancel out. 5y minus 10y is -5y. Be very careful with that. It is a negative. 302 minus 352 is also -50. And y gives you 10. And we're back to kind of where we were before. To solve for x, and I'm just going to do this once this time, Substitute 10 for y into either equation. Let's just use this one that's still kind of untouched and as smaller numbers. 18x plus 5 times 10 equals 176. 18x plus 50 equals 176. 18x equals 126. We've been here before. X equals 7. So, as you've seen, works out no matter what you do with any sort of way with elimination method. Really started with defining the variables and setting up these equations the right way. Number 2, another multiple choice problem. This is the last one of its kind in terms of multiple choice. The next ones will be free response, and there will be a problem in between. Here, okay, I'll preview with you what we have after this. Number 3 is another van bus problem, just like number 2 was. Not number 3, number 6. I'm skipping around. Number 7 is a completely different, whatever number. And then number 10, look at that. School tickets, musical, concert, whatever it is. So these kinds of problems aren't really changing too much. I want you to get the grasp and hearing what it's like again and again. I will go faster with every problem type as you feel more comfortable with it. So let's go with this one. The local amusement park is a popular field trip destination. This year, the senior class at High School A and the senior class at High School B both planned trips there. The senior class at High School A rented and filled 35 vans and 27 buses with 1,643 students. High School B rented and filled 37 vans and 27 buses with 1,669 students. Every van had the same number of students in it as did the buses. That doesn't mean the vans and buses have the same amount of students. That means that every van that holds students has the same amount of students. Every bus fills up their students with the same amount as well. Basically, same size vans, same number of seats, filling them up. How many students can a van carry? How many students can a bus carry? These are the things that we don't know. So for x and y, defining variables, x we will do number of students that can fit in a van, number of students per van. Okay, notice how important this is to define these variables, if not for saying what question am I answering. So x does not equal vans, okay? Y does not equal buses. It's not how many there are, it's not the cost of them, it's not how much they weigh, it's how many students can fit in them. It's very important to be very specific for it yourself as well. Okay, we're going to create two equations. The two equations will represent the number of students coming from each high school. 1643, 1669. Now, once again, the equations that are set up here are not very, again, I gave you very, very simple ones to solve for once they're set up. I'm very aware of that. I probably should have made it harder as I went. Sorry for not doing that. But the fact of the matter is still the same. Got to use elimination method, and you got to set it up right. So, high school A, if you can fit X students per van in 35 vans, 35X, 35 times X represents the number of students in all of your vans at high school A. Take this for example. What if there were 10 students that could fit in each van? How many students are there in all 35 vans? Now you answer the question and you say 350. My next question after that is always, what did you do to get there? And you say 35 times 10. Okay, that's how you got 350. Now I don't know if the answer is 10. In fact, it's not. None of these are 10. I'm giving you an example, and I'm telling you how you should do these problems. Don't confuse yourself with variables. Use real numbers as examples to help you out to explain what it is you're doing. Okay, I'm going to be doing the same thing here with y for the number of students per bus. Number of students per bus times the number of buses, 27, gives you how many students there are in all 27 buses. So if I add all the students in 35 vans and all the students in the 27 buses, I'm getting 1,643 students. Same thing with high school B, 37 vans times the number of students per van, and it's the same for vans, plus 27, of course, like I said, these problems will be set up very, very perfectly for you. 27 students, or 27 buses times the number of students per bus equals 1,669. Now, let's do that subtraction thing like I did last time. I shouldn't add that underline, though. I'm going to take the top equation and multiply by -1 again. You might be asking why I'm not doing the bottom equation. Well, because I am recognizing that 1,669 is greater than 1,643, 35 is greater than 37. As many times as you don't want to use negative numbers, don't. Furthermore, I can rewrite this right under it, right here. And that works out just fine. So all these elimination problems, I know solving the elimination stuff is not going to be very teachable moments. Whoa. These moments are not going to be very teachable. I'm sorry about that. There were other systems of equations videos that I can link to you. I'll feel free to search around for those or practice with those. What is that, 26? 26. X equals 13. So after you do the subtraction, 37 minus 35, 1669 minus 1643, obviously 27 minus 27, we solve for X. That's how many students can fit in each van, 13 of them. Obviously, as a multiple choice thing, I've already answered this question. For the sake of time, I actually might move on because the next problem is another van and bus problem. But to solve for this, 44, substitute 13 into X for this equation or this equation. Heck, you can for this equation as well, and you can solve for Y from there. So let's do this problem one more time. This time it's a water park. What was the other one? Local amusement park. They're always popular field trip destinations. High school A, high school B, obviously these problem types don't change. 84 vans and 34 buses. How the heck does a school do that? I have no idea. 1,926 students, 1,494 students with 48 vans and 34 buses. As you can see, 34 and 34 will line up. We will eliminate just fine. The difference with this problem is it's free response. So this time we have to just make sure that we get the right answers. Okay, let X equal number of students. This never changes. I'm not going to ever stop doing this no matter how many word problems I do for the rest of my life. How many students can a van carry? Number of students per van. Let Y equal number of students per bus. Okay, so if you take the number of vans you have and multiply by the number of students per van for high school A, 84 times X, you will get the number of students in all of those vans. If you take the number of buses taken, 34, times the number of students per bus, Y, 34Y represents how many students in all 34 buses. You add this together, that becomes 1926. That's one equation for high school A. High school B is taking 48 vans times the same number of students per van. That's how many can fit there. And these are different vans. We don't assume the answer is 13 and 44 again. It might be. I have no idea. I haven't done this problem yet. Plus 34 times Y, once again, number of buses times the number of students per bus. In this case is 1,494. Okay, so in this particular problem, as you can see, these numbers are kind of smaller than the numbers on top. So maybe this time I multiply the bottom set by -1 as far as the setup goes. Multiply everything by -1. The only problem with that is when I rewrite it, I'd have to write it underneath. So what I'm going to do here is just I'm going to try and throw in negatives for all these. Basically, I'm making every term negative. That way I can actually cancel out these Y's here. Now, before I do this, let me go back to that first problem that I did right here. I want to emphasize the point that you don't always multiply by -1. You have to multiply by a number that will help you eliminate a variable. So if I wanted to eliminate the Y's, yeah, I multiply by -1. If I want to eliminate the X's, I have to multiply this number by a number that matches with this one. 18x times -2 is -36x. See how I allowed them to eliminate. But you have to multiply everything by -2. All these problems, unfortunately, the way I'm making it happen is you're multiplying just by -1 and canceling. Hey, you got to practice systems the way you do. I wanted to be more cautious about the word problems, give you a couple more, but you've done a lot as is in your, I was going to say in your lifetime, in this year. 1926 minus 1494, don't make me do this. It's six more than 1500. That was 1500 is 426, so 6 more is 432. All right. Oh, I have to divide by 36. Actually, that's not too bad, because 360 is 36 times 10, plus another 36 is 396, plus another 36 is 432. We have to get integers for these things. You can't get a decimal student number. This number is 12. And you're not done with the problem. You have to answer the question. The van can carry 12 students each. And hey, was this the same as the last one? Oh, that was 13. Never mind. Van carries 12 students each. Okay. And once again, this whole plugging it back in, let me make more sense of what we're doing when we're plugging this in. We are actually now helping somebody solve for this by equating this for them. We're saying, hey, the total number of students in all of the vans was this number right here, 84 times 12. So the remaining students that are left must all be equally spread out in the buses. What is 84 times 12? Well, it's 168 more than 840, because that's 84 times 10. So that's 1,008, I believe. If I get an integer, then I'll feel like I at least did the math right. So there are 1,008 students of the 1,926 students that are taking vans. So the remaining lot of them, the remaining 918 of them, are taking buses. And it's the same number of students per bus. How many is that? You divide by 34. Let's see if I can do this one in my head. 34, 680, 1020 minus 34 is, gosh, this is problematic for me. All right, 34 is 986, minus 34 is 952, minus 34 is 918. So that was from 10, 20, 30, 27. There we go. Sorry about that. So van carries 12 students each, bus carries 27 students each. Obviously not the same as the last one where we had, I think it was 13 and 44. Different kinds of buses, or they just evenly spread it out. Or, I don't know, I think if a bus can carry 44 students and you're putting 27 in each bus, you're wasting yourself a lot of money. That's for sure. All right, but there's that problem there. I got 2 more word problems to do for you. This next one's unique compared to the rest of them. Okay, the difference of 2 numbers is 4. Their sum is 110. What are the numbers? Okay, you may use trial and error and guess and check and stuff. In fact, as I'm thinking about it in my head, I think I've already landed on the numbers. That's not the point of this problem. The point is, can you still set it up? Let's define our variables. X equals the first number. Technically kind of the larger number, because if you're subtracting 2 numbers first from second and it's 4, then your first number must be larger. Y is the second number. That's all. So the difference of 2 numbers is 4. If I take the first number and subtract the second number, I get 4. If I take the first number and add the second number, I get 110. That's your setup. Probably the easiest word problem you can do, and probably the one that you're like, oh, I didn't realize you could do it that way. Furthermore, this is already set up for elimination pretty well. Negative, positive. Add them together. 2x, 0 equals 114. See how quickly some of these problems can become? And x is 57. Your first number is 57. What's your second number? Well, you subtract. I mean, you can do either or and plug in one or the other. 57 minus some number is 4. What is that number? Well, subtract 57. If negative y is negative 53, then y is 53. Now, did we answer the question? Sort of. Because you defined the variable, you know how to match these in, but let's write a sentence properly. The numbers are 57 and 53. Now, how can you double check this? Well, you have to make sure their sum is 110. Is 57 plus 53 110? Yeah. So I could do a lot of problems like this, right? We could do these over and over. Difference of, sum of, whatever else. But that whole setup is what's important there. There are some that get a lot harder, though, because you could say the difference of 2 numbers is 4. One number is 2 more than 7 times larger than the other. You know, now you have to do that expression stuff, and hey, that can pop up. That can pop up. I'm more focused on the elimination part for that, but word problems still exist, regardless. Last word problem. The school that Sumali goes to, oh, I think it's a person. I was thinking the school. Is selling tickets for a fall musical. Okay, selling tickets again. On the first day of ticket sales, the school sold 41 adult tickets and 36 student tickets. There we go. That's more people. Still not very many. For a total of $267. The school took in $309 on the second day by selling 55 adult tickets and 36 student tickets. Find the price of an adult ticket and price of a student ticket. Hey, what am I doing? Oh, I'm defining variables. X equals price of an adult ticket. Y equals price of student ticket. And don't think I'm doing this redundantly in like, I can't believe he's doing that again. No, this is a very, very beneficial thing for a lot of reasons. Never stop defining variables. And sometimes they'll define the variables for you. Okay, you sold 41 tickets at X dollars per ticket, or 41 adult tickets at X dollars per ticket. You've made 41 X dollars. That sounds dumb, but what if you sold 10 tickets, which they didn't, because that'd be $410, 41 times 10. But it's 41 times the number. 36 student tickets times the cost of each student ticket gets you how much money you've made selling student tickets. Total, when you add up the amount that you made here for adult tickets, amount of money made here for student tickets, you made $267. These ticket sales must be very cheap, like near like $2 to $5 each, right? Very, very cheap. Well, you know what? I forgot. This is a music. Yeah, that's normal, I guess. 55 adult tickets here times the cost of each adult ticket. Total cost. Total amount made through adult tickets. 36 again. Once again, these always lined up. I really do now regret doing the same thing over and over with regard to saying, hey, multiply by -1. But at the very least, you'll be able to solve these kinds of problems. All right, you have your two systems of equations. Looks like if I multiply this by -1 and rewrite it down here, then I will be in good shape for eliminating my y's. Why? Because these are additive inverses of each other. 36 and -36, they will cancel out. 55x minus 41x is 14x. 309 minus 267 is 42. So x equals 3. Adult ticket. An adult ticket. That is kind of cheap. Costs $3. Remember, the units are important too. It's not just 3. An adult ticket costs 3. Well, 3 what? 3 cents? 3 arms? An arm and a leg. And another arm. Okay, student ticket. You can use either one. This time let's use the bottom one. Let's go bigger numbers this time. On that second day, how much money did they make selling adult tickets? Well, 55 adult tickets times $3 per adult ticket will tell you that exact amount. Then it'll tell you, out of the $309, how much was left for student tickets. So $165 were made selling adult tickets. Subtract 165, and you'll get, oh boy, 144. I think, right? So y equals, divide by 36. That's going to be 4. Y equals 4. What? That is so messed up. Why does an adult ticket cost less than a student ticket? This isn't even senior citizen. I'm not hating on senior citizens. I'm just saying that, you know, they get discounts. This isn't even senior citizen ticket. This is a bad word problem. And student ticket. A student ticket. The real question for this thing is, did the students get ripped off? Uh-huh. That's me. Oh, that's brutal. Especially when the adult, especially like when you go with your parent and they go, I cost less than you, even though they probably paid for both of you. But if they didn't, I think that'd be hilarious. This is a great word problem. Okay. Well, wait, did that happen in the first one? I don't know if I didn't pay attention. Well, see, here's where I was okay with it, because it was like, senior citizen, sometimes they cost the same. I was okay with that. This one here, though, especially when the adult's the parent, probably. All right, so that's it for word problems and furthermore systems of equations. Sure hope a lot of this made sense, though. All right, exponential functions. Sketch the graph of each function. Okay, here's coming in that form y equals ab to the x power. Now, this looks a whole lot like the one I was talking about before when we were using t of n and n for sequence. For geometric sequence. This was when we used t of 0. Now that will make sense there with why I'm going to use that times the common ratio to the n power. So this is the same thing. All right, let's talk about this a little bit. First of all, term 0 is this because at position 0, r to the 0 power is 1. Any number times 1 is that number itself. So term number 0 obviously equals term number 0. For the same thing here, if I substitute 1 for x, and here's actually how you can do all these problems always, of course. You can always use a table. X, y. Plot, graph. Try 0, 1, 2, 3. Stuff like that. You plug in 0. First of all, you do 3 to the 0 power first before you multiply by 1/3. 3 to the 0 power is 1. Okay, that's an important concept I'm going to talk about. Anything to the 0 power is 1. 1 times 1/3 is 1/3. I could plot that point. It's going to be kind of on the small end. I'll do it in red. 1/3 of 1. Maybe about right there. As you can tell, this is 2. This is 1. 1/3. It's more like a quarter. Okay. Substitute 1 into here. 3 to the first power is 3. 3 times 1/3 is 1. So there's a new point here, 1, 1. Next one, 2. 3 squared is 9. 1/3 of 9 is 3. Oh, let's plot these points first. 3 cubed, 3 times 3 times 3 is 27. 1/3 of 27 is 9. Okay, so these points here are 2, 3, right there, 3, 9. Notice how this thing shoots up. Next one, just so you know, maybe you started to notice the pattern. Keep in mind, don't differentiate these from sequences at all. Sequences and sequences and functions kind of both represent the same thing. The only real difference is that in a function, I'm going to connect these dots here. Furthermore, I can go to 0 and negative and everything else, and I'm about to. But don't treat this part any differently here. I'm taking 1/3 and I'm multiplying by 3 a certain number of times. Notice how every single time here, I'm growing by multiplying by 3 one time than the time before. So instead of plugging those things in over and over incessantly, what is the fourth term? You multiply by 3. It's 27. Problem is you can't really fit it on here. I sort of can. 1, 2, 3, 4, 5. It's probably up here. 4, 27. Sure, why not? It's way up there, right? Now to graph this thing, it's going to look like a curve because as you can see, it shoots up. There's no one line that goes through all these. Look, this line, nope, nope. So no one line goes through there. It shoots up. It skyrockets. It's tripling each time x increases by 1. So it goes up higher and it keeps going. And I'm going to try and kind of get it up into that near that 27 area. Whoa, hang on. Let me try that again. Let's do it down from here. I can't go straight. Not bad. All right, it skyrockets that way, right? Taking off. It should be a good-looking curve. Now, it does go both ways. It goes to the right and to the left, which means you can substitute negative values for x to get values there, like x, -1. I'll just go up above x here. -1, -2, -3. Some will get so small that it's not going to matter. In fact, we're probably already at that point with 1/3. A couple ways to do this. I want you to understand both. First one is understanding the fact that, hey, you can raise this to a negative power, to a negative exponent. Raising to a negative exponent does not make your value negative. Raising to a negative exponent is the opposite of multiplying this a certain number of times. It's dividing it a certain number of times. So y equals 1/3 to the, or times 3 to the negative first power. Well, 3 to the -1, a to any negative x is 1 over a to the x power. So 3 to the -1 is 1 over 3 to the positive first power, which is 1 over 3. So that's 1/3 times 1/3, which is 1/9. So you substitute -1 in for x, you're going to get 1/9, positive 1/9 for y. Right here, it's really it might as well be 0, right, as you're graphing it. Really hard to do anything other than just do that. I'll do 2 more either way. -2, substitute that into there. Hopefully you're going to kind of see a connection here. Remember, 0 was 1/3. Y equals 1/3 times -3, or times 3 to the negative second power. That's going to be 1/3 times 1 over 3 squared. Okay, 3 to the negative second power is 1 over 3 squared. So that's 1/3 times 1/9, which is 1 over 27. Okay, so this one here, 1 over 27. Once again, I'm pretty much putting this on 0 at this point. There's really nothing else I can do. But in terms of filling in the table, I want you to recognize something as we're going farther negative. Okay, well, this thing's consistently happening, right? From 0 to 1 to 2 to 3. How about from -3, -2, -1, 0? We should be still multiplying by 3 to get here. Is 1/9 times 3 1/3? You betcha. Of course it is. So times 3 here. So if we're multiplying by 3 down this way, to go this way, we're dividing by 3. So if that helps, or multiplying by 1/3. So if that helps you find a different way to get to these things instead of plugging things in all the time, go with that. Understand that this is a growth rate. I'm going to get you to understand what this value is in 1 second again too. But divide by 3, multiply by 1/3 to get -3. 1/27 times 3 is 1 over 81. Again, way too small to graph, But notice, every time I'm multiplying by 1/3, it's never going to be negative. As far negative as these go, the x's, your y values never become negative. They never become 0 either. They become 1 over a really large number, which is so close to 0, it might as well be 0. It's not, but it might as well be 0. So it never, don't trust my graph. Pretend like my graph never actually touched 0. It approaches it, but it never truly touches it. Y equals 0, the x-axis, is something called an asymptote. It says this is a line, let me actually do the line tool. It says this is a line that is never crossed or breached. It never truly touches it. Looks like that right there. Okay. Now the dotted line, that's not actually a part of the graph. That's a representation for where your graph never crosses. Okay. Oh, the 1/3. This a value is a good starting value. So the next graph that I do, it'll be after the one that I write the equation for. This a value here is kind of like your starting value, just like how y-intercept is starting value for linear functions. This is the y-intercept for these ones. This is when x equals 0. As long as the equation is b to the x power, when x equals 0, this guy goes away. When this guy goes away, all that's left is a. When x equals 0, y equals a. Which is awesome. Now, this goes away because it becomes 1, and a times 1 is a. So the first term I can start with is 1/3. B is the growth rate. This says how many times you multiply by the next time. So the next time I do this graph, I'm going to do it without a table. The next graph that I do. This one we're going to write an equation for the graph, and I'm going to continue talking about that method based on that. However, there are some points that I want you to recognize. So for this one, you're like, how the heck do I start? Start by identifying any points that you see that this thing crosses, but you got to be certain that it's crossing there. So don't say like, it's close to crossing like here. No, it's not. It's definitely crossing this one. It's definitely crossing at this one. It's not crossing at any of these ones over here, so I can't say anything there. Looks like it's crossing up here again at 20. Okay. So what are these 3 points? These 3 points are 0, 5, 110, and 2, 20. So if it helps, you can also put these in as a table. Your perception is your choice as to how you want to make this thing happen. 0, 1, 2. I could even figure out what 3 and 4 are and stuff as well. Okay. So this idea now behind here is like, all right, well, I got to figure out not only where my starting value is, looks like this is it, that'll be a good thing. How much am I multiplying by? Remember, this is exponential functions, and it says what you multiply by and by how many times. Looks like we're doubling it, meaning I could find out that the third position is 40, etc. Furthermore, let's confirm that this works. -1 for x would be the term before this one. So if I multiplied by 2 to get to 5, I divide 5 by 2 to get this number. That would be 2.5, 2.5. Okay, is that 2.5? -1, 1, 2, 2.5. Yeah, that looks pretty good. And I'm sure 340 would have applied as well. Okay, we got our idea of what we have here. We have our growth factor, which means in our y equals ab to the x equation, we know what b is. B equals 2, this growth factor right here. We are growing by doubling our previous value each time. Now, where did we start from? So right now it looks like y equals a times, a times 2 to the x power. To solve for a, you can do a few things. You can either understand what I talked about by starting value, in which case trust that the answer is 5, or you can plug in any x, y value that you would like. And I'll go for the masses here. I'll plug in 1 and 10 to show you that you can do anything here. 10 equals a times 2 to the first power, 1 for x, 10 for y. 10 equals 2 times a equals 5. What if I did it for another one? How about 3 and 40? Ones that I made up. Well, not made up, but drew as a conclusion. 40 equals a times 2 to the third power. 2 to the third power is 8. 40 equals 8a. Hey, guess what? A still equals 5. So a equals 5, that's the starting value, and then it describes how much you're doubling it there on out. So the equation, the final equation is y equals 5 times 2 to the x power. Now, keep in mind, for these equations, I do not multiply by 5 first with 2. No, I raise 2 to the x power first. Then I multiply by 5. Or the way that we'd kind of describe it is starting from 5, this is how many times you multiply by 2 to get to that value. Good equation. Okay, sketch the graph of each function. Whoa. All right, so this one, you're not going to love this one for a lot of reasons here. Now, but let's keep in mind what it is we have. First of all, f of x is the same thing as y, so we're looking at f of x equals ab to the x power. No problem with that. Problem is, not one fraction, but two fractions. All right, I know you're not going to love me for this. Sorry. Let's deal with it. I'm trying to decide if I would like, no, that's okay. I was going to try and change the scales into like, let's make this 1 and this 2. We could, to look at a magnification. In fact, I will in a way. I'm going to go ahead and duplicate this. I'm going to go ahead and say, let's get a second set of this one so I can graph again later. Okay. So I'm going to do two sets of graphs here. One's going to be over here, one's going to be over there. It's going to be the same graph, only I'm going to change the scale of these. So instead, it's going to look like here, it's going to be, this is 1. Okay, this will be 1/2, all right? So this is 2. So just look at the big numbers, not the small ones. 3, 4. Just so you can see a better magnification of what happens as I go down the list. Okay, first of all, this is y equals ab, or f of x equals ab to the x form. So a is 1/4. B is also 1/4. They represent different things, though. A is 1/4 represents the starting value. It's the y-intercept, the value of y when x equals 0. Try it. To the 0 power. 1/4 to the 0 power is 1. 1/4 times 1 is 1/4. So f of 0 is 1/4. This is the value of y when x equals 0. So 1/4 is like way down here. Okay. Now, the only reason I might use a table is to describe how going backwards works from going forward. As I've mentioned before, and I'll plot this on both graphs while I'm here. So this is 1/4 over here. This is 1/4 right here. Which I guess doesn't help much with the magnification too much, but oh well. X is 0, y is 1/4. Okay, going downward, when x is 1, we are going to be multiplying by 1/4 one more time than the previous time. So if you multiply 1/4 by 1/4, you will get 1/16. This is the value. This is the next value. You're multiplying by 1/4. And once again, that's going to be so small here, and here is not going to be much better. It's going to be like right there. All right, so this magnification didn't help as much as I wish it did. But it does a little bit. It shows you the magnification there. That's 1/16. You do it again, you're multiplying by 1/4 again, which is 1/64 again. Might as well be at 0. You're there. Same thing on this one. It's so low down there. And it approaches, it keeps going. It keeps going lower and lower. 1/256, 1/1024, 1/4096. But it never crosses. It never touches 0. It never crosses 0. But those points are not as important to me right now as the next set of points. Having a 1/4 isn't too bad as a growth rate. Fraction, I'm not in love with it. Growth rate, it's not too bad. Why? Because I might be multiplying by 1/4 this way, which, by the way, is the same thing as dividing by 4. So if I'm dividing by 4 this way, what are you doing going to the left? Well, going to the left is x equals -1 and such, -2. Well, dividing by 4 this way, multiplying by 4 going this way. So what's 1/4 times 4? Well, that's 1. X equals -1, y is 1. This one times 4 again, 4. This one here, 16. So it's just going, here we're multiplying by 1/4, here we're dividing by 1/4. And dividing by 1/4 is multiplying by 4. So let's plot some of these points here. -1, 1. -1, 1. -2, 4. -2, 4. And as you can see, I've run out of room on this one. It's just a magnified version. And -3, 16. That's as good as I can get. -4 would be 64. Hey, feel free to plug these in as needed, right? Do what you got to do. Just make sure you know how negative exponents work. Actually, let's do one of them. Let's do -2. Let's do -3 with this one. F of -3 equals 1/4 times 1/4 to the -3rd power. Okay, if a to the x power, if a to the -x power equals 1/a to the x, then 1/a to the -x power equals a to the +x. So, as I have this guy right here, this is 1 to the -3rd power, which is 1. 4 to the -3rd power down here, let's bring this down. Okay, this will be f of negative 3. It's equal to 1/4 times 1 over 4 to the negative third power, which is 4 to the positive third power, which is 64, which that gives you 16. So once again, you're getting 16 there again. So, your choice on what you want to do. If you want to use a table, great. It might take a long time, though. If you want to use points like this, go ahead. Now, keep in mind, when you take the final, it's going to be a multiple choice final. So it's not like you have much wiggle room in terms of being super creative here. But you get to observe the different graphs and say, hey, which one refers to what it is that I am talking about? Now, both of these are the same exact graph, but like I said, one's a different magnification. And its asymptote is still y equals 0. It's still this x-axis right here. It will never cross this or this one in this case. And I can magnify it as much as I want, and I can still find points as I keep going down. One last one, write an equation for this graph right here. Once again, find the points you have, determine what your growth rate is, all depending on that, and then, continue from that. So it looks like these are 3 points I can plot for sure. So let's go ahead and write out what those 3 points are. It's negative 2, comma 12, negative 1, comma 6, and 0, comma 3. As an XY table, negative 2, negative 1, 0, 12, 6, 3. So it looks like you're dividing this time. Now keep in mind, you can call this dividing, but make sure that you understand what dividing is the same as when you do multiplication. So, okay, yeah, I'm dividing by 2. Big whoop, want to fight about it? But dividing by negative 2 is the same as multiplying by 1/2. The important thing for that is we're not going to be putting over 2, well, we sort of are because it's over 2 here. But in our equation, this is your b value. B is actually 1/2, not just divided by 2. We are multiplying by it. Remember, it's y equals ab to the x form, like so. So if b is 1/2, what is our starting value? Well, we've talked about this before. This a value right here, it's when x equals 0. For the sake of time, I'm just going to go ahead and tell you, a is 3. It's your y-intercept, value of y when x equals 0. So we have the equation, and I think we'd be done with that at that point. I want to show you a few more points that you can find, even despite the fact that it's 1/2, to confirm that you're correct with this equation. Let's find out when x equals 1 what y should be equal to. Well, you're going to be dividing 3 by 2 or multiplying it by 1/2. That's 3 over 2. That's also 1.5. Okay? 1.5. X equals 1. Y is 1.5. Yeah, that was about right. 1.5 right there. Yeah. Divided by 2 again. 1.5 divided by 2, $1.50 divided by 2 is 0.75, 75 cents. 3/4. Yeah, that's 3/4. So you can see where that happens. You plug in negative 3, what would you get? Well, you're going to divide by 1/2, which is doubling 12, which is 24. So that would have gone just up here, and you can see where that probably would have happened as well. So, yeah, this graph all checks out. And remember, this never crosses that threshold there. Keeps on going forever. So there's your last exponential function we're going to do. Okay, graphing inequalities, systems of inequalities here. All right, let's talk about this a little bit. Greater than, less than, or equal to. What do these have to do with it? I'll talk about them in a second. Let's first set these equal to them, because I want to talk more about graphing the lines first. I think we got to practice graphing lines, right? Now, these are written in what's called standard form, and there's nothing really wrong with standard form other than, even for myself, I can't visually look at this equation and say, I know exactly what this graph is going to look like. You can plot points easily from here, most notably the x and y intercepts. Okay, I'm not going to do that right now. I will set these into y equals mx plus b form. To do that, subtract x from both sides. You'll get 3y equals negative x minus 6. Divide both sides by 3, which means divide everything by 3. And you will get y equals negative, remember this is a negative 1, negative 1/3 x minus 2. Don't be too alarmed by that fraction. Fractions for slopes are actually not bad. It's actually a good thing. So how do you graph it? Start from 0, negative 2, that's your y-intercept. Take this, go down 1 over 3. Go down 1 over 3. Can't really fit it, but there would be about another point. Up 1 to the left 3. That's still negative 1/3. Up 1 to the left 3. Yada, yada. Okay. Graphing this here. Get my 2 arrows. And make it green. Oh, this is already set up for me. Perfect. And go ahead and go through those lines as best as I can. That looks pretty good. Now we'll talk about what the less than or greater than stuff means right now. Okay. So I had this y equals stuff here. Now I did change this from an inequality, but the thing about inequalities is you still do compare things in such a way that you have to keep both sides balanced. So subtracting x divided by 3 was not a problem. Now as this was greater than, this will also be greater than, this will also be greater than. So your equation is actually an inequality, and it says y is greater than negative 1/3 x minus 2. What does that have anything to do with it? Well, first of all, you are comparing a y value to the line at some x value. So let's say I plotted a point, and let's do a more difficult point first. We'll do an easier point next. Let's check this point, negative 2, 3. That's negative 2 for x, 3 for y. What I want to check and see is when I substitute 3 for y and negative 2 for x, am I getting a true statement in this inequality? Is 3 greater than the number that I am doing this with? Negative 1/3 times negative 2 is positive 2/3. 2/3 minus 2 is negative 1 1/3, I think. 3 is greater than negative 1 1/3. Yay, that's true. Yay, this one's true. This statement is true. So will anything on this side of this line, okay, including the point 0, 0. This is the easiest one to double check with. As long as your point is not on the, as long as the origin is not on the boundary line itself, this is the point you should probably always double check things with. Why? Because despite the fraction issues, this is 0, this is 0. 0 is greater than 0 minus 2. 0 is greater than negative 2. Is that true? Of course it is. Very easy to double check with because these terms just kind of go, the terms become 0. They kind of go away in a way. Everything on this side of this line will be true. Everything. Now, what if I tried something that was on the line? What if I tried 3, negative 3? Let's see if this will give me a true statement. Something on the line. Negative 3 is greater than negative 1/3 times 3 minus 2. Negative 3 is greater than, negative 1/3 of 3 is negative 1. Negative 1 minus 2. Negative 3 is greater than negative 3. Is that true? Never. Nothing is ever greater than itself. False. I was starting to write true. False. This thing on the line is not true. In fact, everything on this line is not true. When it's only greater than and not greater than or equal to, it will always be false. So what we have to do to graph this is not just draw the boundary line. This line is the threshold to say what are the true statements with what are the false statements. And I want you to believe for me just right now that if I picked any point down here, it would have been false. I'm going to save you some time here. So there are two things we're going to do to represent that. First of all, the boundary line. Boundary line is going to be a broken line like this. Dashed. Anything like that. Okay? Make it a little bigger. There you go. Look at that. Broken line. Broken line doesn't mean if it's on this part it's good, if it's on this part it's bad. No, anything on the line says it's false. The broken line is just an indicator of that. Second thing we're going to do is shading. Now by shading, I mean actually, look, if anything here is true, why plot a bunch of points? Instead, just do a whole bunch of shading there to say anything above this line will be true. That's how we graph this first inequality up here, x plus 3y is greater than negative 6. Getting it into a proper form to graph, a good form for you that you want to graph. You can do whatever you want, including a table. Go ahead. Or the x and y intercepts. But get your line, draw the boundary line, and then figure out whether it's supposed to be broken or solid. If it's solid, it means it includes the line itself. If it's broken, it means it does not. And the way we shaded really was we shaded above the graph because the y value that you're comparing to the line at that x value is greater than it always. So at negative 3, at 3 for x, we have to plug in values for y that are greater than negative 3. Any of these ones. And at 1 for x, we have to plug in values for y that are greater than whatever that number is. Negative 2 1/3, I'm sure. Any of those would be true, including any of these. Any and all. Okay? That's what we're doing with the graphs. Now, we're not done with this thing, not even well, we're halfway done. I won't spend quite as much time talking about the other one, but I will talk about that double checking with 0, 0 each and every time. And I'll show you what it does with some other problems to help double check this stuff. 2x plus y is less than or equal to 3. First I set it equal to. You do not have to set it equal to start with. I'm just telling you that this is how we're treating it. It's the same thing as balancing an equation. I'm subtracting 2x from both sides, by the way. And there's your equation right there. Y is equal to negative 2x plus 3. Now, as this was a less than or equal to problem, this remains as a less than or equal to problem. So this is a less than or equal to problem. So now we have less than or equal to negative 2x plus 3. Now, as we graph it, you know what, I might have spoken too soon. Let's keep this as equal to as far as graphing it. I think that's the main reason why I want to do that. As far as graphing it here, y-intercept, slope. Negative 2 is negative 2 over 1. Y-intercept at 0, 3. Negative 2 over 1 looks like this. Down 2 over 1, down 2 over 1, down 2 over 1. Where they intersect is not going to be anything more other than a threshold for our 4 regions. What regions am I talking about? Oh, you'll see. Oh, yeah. You will definitely see what I'm talking about here. And I'm being serious. You will. So here, I graphed this line right here. And now you've created 4 regions. Region number 1, region number 2, region number 3, and region number 4. That point of intersection does nothing more than that for us in this case. If this was solving a system of equations by graphing, all right, well, the system solution would be, I guess, 3, negative 3. All right, x equals 3, y equals negative 3. What that means is if these were equal signs, plugging in 3 for x and negative 3 for y would give us a true statement for both of these. That's not what we're looking for. We're looking for the infinite number of points in what region will give us that. So how do we do that? Now I got to start doing my shading and everything here. That's where the less than or equal to will come into play. So if I said greater than represented shading above the line, which by the way, this would have been above the line, then less than must mean shading below the line. So my shading probably is going to end up looking like this. Now I want us to see if this is what it's going to be by testing 0, 0 as a point. Now, if I plug in 0, 0, I expect a true statement out if I think I should be shading underneath. Let's see here. 0 for y, 0 for x. This becomes 0. 0 plus 3 is 3. Is 0 less than or equal to 3? Well, it's less than it, so a true statement this one is. So is anything else under the line. So when I shade it, it's going to look like this right here. A big mess. Now, I haven't mentioned the boundary line much. How come mine is solid this time instead of, well, not solid? Because, well, instead of broken. Because this time it's less than or equal to. What if I test a point on the line? What if I test the point negative 1, 5? You see this one's on the line right here. Let's try negative 1 for, which number? Negative 1 for x, 5 for y. Is 5 less than or equal to negative 2 times 1 plus 3? I'm sorry, there's negative 1. 5 is less than or equal to 2 plus 3. 5 is less than or equal to 5. That's true. 5 may not be less than 5, but 5 is certainly equal to 5. You only need to satisfy one of these, less than or equal to. So it's equal to it, so anything on the line is true. So our visual representation to say things on the line are true are making it solid just like we would any other. This one stays broken, which means anything on it is not true. Now, we're almost done with everything. The last thing I need to do is get the full-on shading of what one satisfies both inequalities, meaning what region. This region, this one, or this one. So as you can tell, this region technically satisfies neither of them. I plug in any point that's anywhere under this line and above this line, I'm going to get a false statement for both inequalities. This one right here, this region, will only satisfy the bottom inequality, but not the top one. The green right here exclusively will only satisfy the top, but not the bottom, whereas this upper left region, including the point 0, 0, will satisfy both the top and bottom inequalities. To double check, I'll do one more, I promise. I'm going to do one that's going to give me a good fraction, otherwise it's going to be a little messy. Let's do negative 3, 6. We know this is a part of it, right? This is still within the region. Negative 3, 6. So let's substitute negative 3, 6 into both inequalities here, erasing some of this work. Sorry. Let's do it with the original inequalities this time. Let's do a better double check with that. Last time when I did my substitution, I substituted in these. That's probably a bad one to do that with because this was equation manipulation. We want to test with the original inequalities. Okay, -3 for x, 6 for y. Is 15 greater than 6? You betcha. That one's true. Okay, bottom equation. -3 for x, 6 for y. Is 0 less than or equal to 3? Of course it is. So that one checks out, and anything in this region will check out. So what's the best way to do the shading for all this? Get this scribbly stuff out of the way, at least for both sets. You should only really do one scribble by the very end. So maybe do light scribbling beforehand, and I think I can actually do that. Check this out. If I take this and make it more transparent, I can make it look, oh, look at that. Light scribble, light shade, yeah. So anything within the shaded region, including anything on the red line, not the green line, but anything on the shaded region and red line will satisfy both inequalities always. That's your answer. That's how these will be sketched. Now, this is number 1 of 6 inequalities, so I will not spend as much time talking about the other ones unless there are new things to talk about. And trust me, there will be new things to talk about. I don't know if it's appearing in the next one. The very first thing I did, though, was rewrite it from standard form to slope-intercept form. I think that was a big step. I will be testing 0, 0 each time. Moving on. Okay, here's number 3, and here's an example of something that looks a little bit different. In what way? Actually, there are 2 ways. First, in both equations. Both equations have 2 different things here. Okay, the first inequality, they're called inequalities. The first inequality, let's change it to equals just for a second, so we can get the line graphed again. Subtract x from both sides. Divide by -2 from both sides. Let me write the divide by -2 so you can really see what I'm dividing by here. Divide by -2, divide by -2. Remember, this was a -1, divide by -2. -1 over -2 is positive 1 over 2, so this becomes, 1 second. Come on, there we go. So this becomes 1 over 2x, 1/2 x, minus 2. All right, there's an equation of a line I'm going to graph. Starting from -2, we go up 1 over 2. Not going to spend a lot of time talking about those ones. Those graphs we should be able to know how to do pretty well by now. Okay, draw the line. Blue. All right, it's going to look about like right here, like that. Now, keep in mind the original one was greater than, so as we stick to greater than here, we stick to greater than here, we stick to greater than here. By that I mean this will be instead a broken line, not a solid line. So we already know that, and considering what I talked about before, we will be shading above right here. And as we test this shading, okay, so shading is going to look like that. To figure out whether we shaded in the right place by shading above because this said greater than with y, let's test a point that will always work very well with this, 0, 0. It's not on the boundary line, and it's within the shaded region. I'm going to test this. This time I'm going to test it with the original inequality. Sorry for not doing that last time. Really should do it every single time. Let's test this and plug in 0 for x, 0 for y, and see if we get a true statement out. I expect a true statement by the way that I shaded. 0 for x is 0 minus 2 times 0 is greater than 4. 0 minus 0 is greater than 4. 0 is greater than 4. True or false? True. Uh-oh, we messed up. Okay, this is false. So what happens here is you say, this is why we double check. Why did we do this greater than thing every single time? Because we say to. Because we say it's just like an equal sign, only you put the greater than each time and this and that. There's one difference in this problem compared to the other problems. And if you can scout it, this thing should be less than, not greater than. So it should be shaded over here. But what's the difference? The difference is we divided by a negative number. And when you divide or multiply by a negative number, your inequality flips. Instead of spending the time mentioning and talking about why that is, I need you to trust it. And if you don't trust it, always double check your work, because every time you double check and you expect something to be true and you get false, or expect something to be false and you get true, then at least you can switch it. And that's all you got to do. So like, all right, we switched it. It's okay. We double checked. We found out we were wrong. We switched it. And there it is. So this should be the true inequality where it becomes less than after you divide by the negative. Once you do that, it changes. Now it is still a broken line. We just shaded underneath. We're good. Next one has its own little unique thing. This says x is less than or equal to 2. And I know some people have some trouble with these, so let me kind of break this down in a couple ways. I'm going to do a table for this. I'm going to first do it for x equals 2. Now, I can't do y equals mx plus b because there is no y. So I'm just going to go ahead and create a table with this x and y and figure out what x is going to be when y equals something. Keep in mind, this time y is no longer the dependent variable. Now y is the independent variable, meaning I choose values for y to get values for x. If x equals something, even in terms of y or not, let's plug in numbers for y. When y equals 0 in this equation, what does x equal? Substitute 0 for y, oh, x equals 2. 1. Substitute 1 for y, oh, x equals 2. 2. 2. 3. 2. 4. 2. 5. 2. Negative 1. 2. 1,000. 2. Pi, 2. I'm being a little facetious. Kind of funny. What I'm saying is no matter what y equals, x equals 2, because y is not in the equation. Y is not helping factor with anything. So no matter what y equals, check out what all these points are. 2, 0, 2, 1, 2, 2, 3, 2, 4, 2, 5, 2, negative 1, 2, 1,002. What does this line look like? It's vertical. All right, this line is vertical. X equals 2 is the line for x when it equals 2. And that's exactly what it is. And people get more confused with it than normal because they are following a process so much that they forget that it's not just about slope-intercept form all the time. Sometimes it's about what it means. No matter what, y equals x always equals 2. And that's what the line looks like for x equals 2. Now, keep in mind, this was an inequality that said x is less than or equal to 2. So we're going to keep it as x is less than or equal to 2 right here. So how do we graph that? Well, less than or equal means it's going to be a solid line. Less than, for x, we're comparing a number for x that's less than 2. That might mean 1, 0, negative 1, negative 2, any of these. So anything to the left will work here. So we're going to shade this way. So as opposed to the original y equals whatever, y is less than or greater than, we are comparing the value y to it. This time we're comparing the value x. So whereas for y we'd be shading above or below, now this time we are shading to the left and to the right only because this is an x in comparison. So once again we have 4, oh, you can test 0, 0, but 0 for x is less than 2. That works. So we have 4 different regions here. We have to figure out which region contains both of them, and it's the ones the cross section of both. I'm not going to double check a value for now. Let's go ahead and say that, yeah, that's true. So let me delete this kind of mess here of the blue and the green. Let's draw this shaded a little bit better. Let's use a little transparent version right here. Shade over here. This is the solution to this. And again, what this means is any point in this shaded region for here and evermore as this splits apart, including anything on the green, that I plug in for x and y into these inequalities will be true for both of them. That's all that means. That's all we're trying to do for this whole thing. So to keep it short, there's more than one answer. There's an infinite number of answers, right? If this was if this was equals and equals, there would only be one answer. It would be this one. Okay? But this is a comparison to these values. So there's an infinite number of answers. And if you've been in my Algebra 1-2 class, then you've practiced the word problems with them. And you saw how they made real world sense. Okay? All right, number 5. I'm going to speed this one up a little bit more, but you're going to see how I'm going to be able to switch something and trust it. I'm always going to plug in 0, 0 as I do it, though. First one, this time I'm going to keep the inequality there. X minus y is less than 2. Subtract x from both sides. Negative y is less than negative x plus 2. How do you solve for y? Divide by negative 1. Now, we just divided by a negative. That does mean that the sign switches, that the inequality switches. All the signs switch as well. Y is now going to be greater than negative x over negative 1 is positive x, plus 2 over negative 1 is minus 2. Y is greater than x minus 2. And if you don't believe me, we'll still double check and see. Let's make this purple so I can graph in purple. Okay, graph in purple here. Now keep in mind this line is going to be broken because it's greater than here. We're going to start at negative 2. Hang on. We're going to start at negative 2, 0, negative 2. X slope is 1 over 1. Up 1 over 1 looks like this here. Down 1 to the left 1 looks like that. And our graph will be this line. Perfect. Now, shading, greater than, we should shade above. How can I double check that? Let's plug in 0, 0. Now keep in mind, I'm not plugging in 0, 0 because it's in the shaded region. I'm plugging in 0, 0 because it's an easy one to do. Now when I plug in 0, 0 into the original inequality, I expect a true statement because that's the side I shaded on, the side with 0, 0. 0 minus 0 is 0. 0 is less than 2. That's true. Cool. I shaded on the correct side above the line because it's greater than. Not less than anymore. Divided by -1, right? I could have multiplied by -1. I still would have flipped the inequality. Okay, this one right here. And as you can see, these problems kind of become more the same. That's why I'm considering just going faster and faster as time goes on. Pretty much to the point where you're saying, I'm just checking to see if I got the right answer, right? The explanation, the same thing. Subtract 2x, divide by 3, -2/3, oh, whoops, less than. -2/3 x plus 3. So once again, a graph. Let's get out of these problems here. Down 2 over 3, down 2 over 3. About over there. Up 2 over 3 here this way. Broken line again. Okay, both of these are broken. This one, though, is like that. This one is less than, so I'll shade on this side. Testing 0, 0 should give me a true statement again because 0, 0 is in the blue shaded region. That's nice. Thank you for doing that. All right, so testing 0, 0. Again, why am I testing 0, 0? I keep asking you, why am I testing that? Well, because 2 times 0, 0, 3 times 0, 0. This is all 0. Is 0 less than 9? Yeah. So you don't have to calculate I'm not trying like -4 or 3, and I got to do 2 times -4 plus 3 times 3. No, it's going to take way too long. Test 0, 0. It was true, and I expected it to be true. And that works. So my shaded region is going to be right here. Now, again, the dotted lines, the boundary lines, this is not a part of the shaded region. Meaning I can go to 0, 2.9. That'll give me a true statement. 0, 3 will not. Same with nothing on the purple. But this shaded region will give me everything true that I need. Very nice. All right, let's just move on. Let's keep going. Let's do this thing. Subtract 4x. Divide by -3. Now I'm dividing by a negative. What's going to happen with that inequality? Switches. Y is greater than 4/3 x minus 1. Okay? Start at 0, -1. Go up 4 over 3. Down 4 over 3. Graph that line, greater than, not greater than or equal to, and once again, broken. You're going to get a lot of broken lines, apparently. Okay, I'll fix that a little bit. Okay, as I flipped it, it was greater than, and I should be shading above. Let's test 0, 0 and see if it works. Again, if I test 0, 0, looks like it'll be true. 0 minus 0 is 0. Is 0 less than 3? You betcha. So I shaded on the correct side. Okay. This one right here, I'm going to do this one differently, just to shake it up now because I've been talking so much about the same thing over and over. This time I'm not going to graph it in slope-intercept form. I will set it to equals just so you're feeling a little more comfortable about the problem again, though. Here's how standard form is nice. You can find x and y intercepts really quickly. How? The x-intercept is the value of x when y equals 0. So how do I do that? Substitute 0 for y. -3 times 0 is 0. So x equals -6. Wow, that was fast. So -6, 0. Here's the problem. It's a little off the graph here. But here's a point. Now why is this so good? Because for a line, you technically only need 2 points. So why not do the x-intercept and the y-intercept? I don't know. So let's see. Y-intercept is the value of y when x equals 0. So substitute 0 for x. Well, 3y equals -6. Divided by -3, y equals 2. So you got another intercept, 0, 2. Boom, right there. I have 2 points, and I make the line. Now, I know it's going to be broken, so I'm just going to make it broken for now. Anyway, I'll shade in a second. But here's what it doesn't do. it didn't help me figure out where my inequalities kind of go, right? It didn't tell me whether to be above or below the line. We could test 0, 0 and figure that out. But I'll do that now by doing slope-intercept form with you and showing you that this line is exactly... Okay, so what do we expect this line to be? Y equals something x plus 2, right? We need a slope. Let's see. It goes through this point, so it goes up 1 over 3. So I expect y equals 1/3 x plus 2 to be the equation. Or y is, what is it, less than? Well, actually greater than. Or equals, right? Equals. So x minus 3y is greater than negative 6. Negative 3y is greater than negative x minus 6. Divide everything by negative 3. So y is now less than 1/3 x plus 2. So there it is. So we expected that. Now it's less than. This is where I needed to check the graphing stuff. So I guess when I was talking about standard form, it didn't really help out talking about it because we didn't know where to shade it. But I was helping you with how intercepts kind of work and what we do for that. Now, how do we double check this? Let's plug in 0, 0 into the original equation right here. 1 second. Okay, 0, 0 into this inequality. 0 is greater than negative 6. You betcha. So this is true as well. So the shaded region that occupies both of them is down here in this bottom one right there. Let's go ahead and shade it and call it a day for number 7. Once again, you know, I'm getting kind of tired of doing the problems. Not tired of doing them, but I don't think I have anything more to explain. Right? Now I'm just solidifying them for you. A lot of them are less than now. There's no more less than or equal to. That's a bummer. All right, this one should be pretty quick, though. X is less than 3. Hey, we just talked about what x equals 3 should look like, or let's talk about what it should look like. Vertical line at x equals 3. Now, it's dotted because x is everything less than 3, not including 3. Less than 3 is everything to the left, including 0, 0. There's that one. Okay, this one right here. X plus 3y is greater than 6. X plus 3y greater than 6. Subtract x. Divide by 3. Nothing switches. I didn't divide by a negative. So it's going to look like that. Negative 1/3 x plus 2. Start at 2. Go down 1 over 3. Down 1 over 3. And up 1 to the left 3. Okay. I'm sorry for speeding up now. After I've done so many of these problems, it's kind of like, you know, where do you go from here? Right? So this one, boom. It's also dashed, right? Shading above because y is greater than. Now this time, okay, here's an example of testing 0, 0, getting a false statement and expecting one. If I test 0, 0, the red is obviously not in the green. I expect it to not be in the green. 0 plus 0 is 0. Is 0 greater than 6? No. I expected it not to be because 0, 0 is not a part of the solution set. So finally, you get one where I'm testing 0, 0. It doesn't become true, and I wanted that because that was my desire. The shaded intersection of both of these appears to be right here after we saw that cross part, and that's it. So graphing these once again, there's no one point. There's an infinite number of points. Okay, there is an infinite number of points. I'm going to reemphasize that over and over and over again. Make sure we got that one nailed down. Okay? I mean, and if anything else for all these problems, really what you're practicing also is how to graph lines, how to test points, how to convert things in y equals mx plus b form. So, you know, other things are being practiced. It's not like this is a total waste. And I mean, I wouldn't call this a total waste. I'm not wasting anyone's time. All I'm saying is that, look, I'm doing the same problem over and over. And just like the word problems, I felt kind of bad that at the time when I was doing them, by the way, just going to tell you, you can also multiply by -1 here, not just divide. But as you multiply by -1, same thing, inequality flips. You know, I felt kind of bad that it was just the same, you know, same setup. The elimination stuff wasn't any more of a challenge. And I'm sure you're like, well, I don't like challenges anyway. Well, the final might pose challenges. So you got to be familiar with that. And a lot of different problems you're going to face in your life in math. Got to be ready for any of them. In fact, I'm going to tell you right now, I believe your final probably includes a problem where your word problem has decimals. You know, where we're talking about dollars. Well, there are dollars and cents that are included with word problems as well. So be ready for any of them, right? Anything can happen here. As long as you have a calculator and you can trust your math and work that you do, by all means, go ahead, right? Be ready to do that. All right, now I didn't talk through this problem as I was doing it, but hopefully you kind of watched what I was doing. I solved for y here. Well, what y could be. It's a less than, so it is underneath right here. If I tested 0, 0 in this inequality, is 0 greater than 3? No. So 0 did not expect to be true. It's not a part of the solution set. I'm good. Broken line, less than, good to go. Next one right here, just subtract 3x from both sides. You get y is less than or equal to negative 3x plus 1. Finally, we got a less than or equal to again. Another solid line. Awesome. And this is the last one we're going to do. Down 3 over 1. Down 3 over 1. What I liked about all of these, which I think was always true, is these always did cross at an integer point. Not sure if they meant for that to happen. I don't know. But if these were equations, like, so basically if this was a system of equations and you had to solve for x and y, we could have found all of those as well, right? I could have practiced that with you. Like, what's this system of equations? Or what's the solution set? If this was equal to and equal to, this solution set would be 1, negative 2, right? But for inequalities, we are shading. And as we shade, let's go ahead and shade this one, less than or equal to, shading underneath. Yes, this is underneath this line right here. If I test 0, 0, would that be a solution? Yeah, That one right there? 0 plus 0 is, what was it, less than? Is less than or equal to 1. Is 0 less than or equal to 1? Yes. Barely is, but it is. So that one works as well. What's the shaded region? It's this one down here. That's the solution to both of these. So as I'm doing my very last one here, let's go ahead and give it a nice purple, as that's a blend of red and blue. Faded purple. Let's go ahead and shade it. That looks nice. Now, that includes everything in the shaded region and everything on the blue line, because the blue line is solid. If I tested any of those, that would work as well. But I am done with it. No more. That's graphing inequalities. Hopefully, you have gotten used to it. Now, there might be a question on this stuff that says, is a point, it might not say graph them. It might say, is the point 4, negative 2 a solution to this system? And they might give you that. Maybe you have to graph it and check or plug the points in. Obviously, the answer is no. Is the point 1, negative 4 a solution? Yes. All right, so, just be ready. Okay, I got 2 more sets of problems. They're both kind of bigger problems because it's linear regression. I might have to do some explanation through it. I might have to do some calculation as well. They give us the equation stuff, but you're going to have to be able to know how to kind of do it or what it all kind of means with it. With the help of scientists, farmers in the United Kingdom have been able to produce more and more grain per hectare each year. Is that like an acre? Hectare. I'm calling it hectare. Here are the crop yields for several years. All right. Now, look, I don't even understand what this means. But we should still be able to describe what's happening. As the years go on, there's a larger yield, crop yield of kilograms per hectare. Okay? The crop yield can be described by the equation y equals 81x minus 156,000, where x is the year and y is the grain yield in kilograms per hectare. So, a couple things. First of all, isn't it nice that they defined their variables? Look, they wrote an equation. They defined their variables. X is the year, y is the grain yield in kilograms per hectare. Second thing, and this is actually really interesting that they did this. The x value is literally the year, meaning the year 1964 is the year 1964. Do you remember when we had those problems, like where we did it like this, but we treated a year as like year 0, and this would be like year 3 and year 11, stuff like that? Well, unfortunately, it looks like these problems aren't that, which means your y-intercept, here's the biggest thing I want to say about this. Your y-intercept is not right here, because this is not the value of y when x equals 0. This is the value of y when x equals 1950. Okay? 2 way different things. The y-intercept is the value of y when x equals 0. So that'd be like year 0. And that's what we're going to be representing right here, which is maybe an unrealistic thing. All right, but we'll be talking about why linear equations are exactly what they are and why this regression stuff is such a small sample size it can't model and extrapolate all the time. We can sometimes only interpolate, and I'll say what those 2 numbers mean, or what those 2 words mean in a second. So here are the points. Remember, this was X, this was Y. They plotted them. They graphed them for you. They gave you a trend line. They gave you an equation. If you need to know how to do it, I'm not sure if I can say much about it because I can't show you a calculator. But you have to enter data in a table and go and find the linear regression equation information. Okay, the slope of the line represents what? Okay, 81. 81 is 81 divided by 1. 81 is the rise, 1 is the run, which means every time I rise 81 here, I'm running 1 here. Rising is yield of kilograms per hectare. Hectare. I call it hectare. X is the year, or the run is the year, which represents the number of years that have passed. So the amount of yield per year. The slope of the line represents this. Every year, fields, farmers in the United Kingdom, farmers have produced approximately an average of 81 more, more, so an increase, kilograms per hectare. Boom. I was going to say per year, but I already said that. Every year. So every year, the yield of kilograms per hectare increases by 81. That's an average. Okay, which means we're going to have to do some predictions here. We're going to do some of this stuff, right? What does the y-intercept of this function represent? Okay, so this is where stuff gets really weird because this graph does not show where x equals 0. Look, this is the year 2000. 0 is all the way over here. We can't even see it. I could even do this line right here. Hey, look, it's already blue. I could do this line all the way down, really far down here. I could even zoom out. I'm still not going to be finding year 0, right? But it's way the heck down there, right? It's not quite on the line, but you get the picture. The y-intercept is way down there, which means the yield was going to be way lower than 8,000. In fact, it's going to be a negative number, I bet. Okay. What is the y-intercept of the, oh, it is. We already have it. It's right here. Y-intercept. Y equals negative 156,000. Okay. That means there's a point on this graph that is 0, negative 156,000. What this means, and I know it's an unrealistic thing, that's why extrapolation is not always the best case for this. The y-intercept of this function represents that in the year 0, in 0 AD, or BC, or whatever, I think 0 AD, in 0 AD, right, when Jesus Christ was born, right, as B is before Christ, BC is before Christ, when Jesus Christ was born, farmers yielded negative 156,000 kilograms of hectare per year. Isn't that crazy? Farmers produced negative 156,000 kilograms of hectare per year. Okay, this was not a great y-intercept thing for this problem, especially because they didn't say let year 0 equal, or like let 1960 equal year 0. I would have much preferred that and done a slope with that. You know what? We didn't. We can't. Let's move on. That's fine. So this is unrealistic, right? It's stupid. You can't have more. You can't have less than 0 kilograms of it per year. You can't have a negative number, and this is a way beyond negative number. So this means a couple things. First of all, you can't represent a linear model for everything. Second of all, this linear model for this set of points doesn't predict that. And third of all, I mean, sometimes these things just don't work the way they're supposed to, right? You can't extrapolate all the time. You can't assume outside of this thing for everything. All right, we have one interpolation question and one extrapolation question. This is the interpolation question. This is the extrapolation question. What's the difference between the two? The year 1983 is within the bounds of the points that we chose. This is from 1964 to 2006. Well, 1983 fits right here. Interpolation is a much better route for success for your stuff because this fits within your data and it will be on your prediction line. Remember, 1983 is about right there. This is the number we're about to predict for our answer. It's going to be just under 5,000. That's okay. The year 2026, I think it said. 2026 is extrapolation. That is outside of our data range. Here's year 2006. This is 20 years later. So once again, dangerous predictions occur outside of the extrapolation measure. And I don't mean dangerous like this is lethal, but you can't trust it. You can't trust it as much as something that's inside. But hey, we're going to do both. We're going to do both for the next problem I do as well. Let's do it. Now, 1983 is the year for X. It's not years since 1960. No, it's actually the number we're going to plug in. This is where I'm going to have to use the calculator. In the year 1983, what was the crop yield? Meaning how many kilograms per hectare of grain is it? So, to do that, I'm going to use my original equation, y equals 81x minus 156,000. Okay. From the year 156,000, I'm going to add 1,983 times if we're talking about the sequence stuff we did before. I'm going to substitute 1983 for this. This is one of those arithmetic sequences in explicit form, right? 81 times 1983. I'm never going to try that one in my head. That is 160,623 minus 156,000 should equal, I'm just going to go and do it here, 4,623 kilograms per hectare of grain expected in 1983. Okay, one thing I do want to mention about this, because this is not here, is residuals. Okay. Well, I should have done it for a different year. But the year 1983 is right here. This is what is predicted. Okay? This is what we can predict. This is not necessarily what the exact value was. What if the exact value was 5,500? What if in 1983 there were 5,500 kilograms of kilograms per hectare of grain? Okay, well the residual, I'm just going to mention it once because it's not a question anywhere on here. The residual of something is the actual minus the actual value minus the predicted value. Ugh. The actual value would have been 5,500, let's say it was, minus the predicted, which was 4,623. So the residual there is 877, okay, which is just some error. This says this is how many kilograms of hectare we were off, and we undershot it. If the actual was above it, then your residual will be positive, which means we undershot with our prediction. And hey, predictions only are what they are. This is a straight line. Look, the line didn't go through all of these points. It probably didn't go through any of the points. But this line is the best fitting line for this data, and that's where we're going to do our predictions for. So 877 is the residual. That's how much we'd be off for an actual of 5,500 in the year 1983. Not that that's what one of our questions were, but let's go and move on. Extrapolation, this time it'll be the exact same thing as we did with interpolation. I'm going to substitute 2026 for this thing right here. The only thing about extrapolation, though, is that you can't trust this number as much because it is outside of your year range that you're talking about. You can't make predictions for anything outside of our year ranges, guys. We can only do the best we can with our models. 81, hang on a second. 81 times 2026 is 164,000. 106. We're going to subtract 156,000. And that'll give us, I think, 9,106 kilograms per hectare of grain in the year 2026. So, as farmers are yielding an increase of an average of 81 kilograms per hectare of crops per year, in the year 2026, we are expecting about right there in the 9,000 range. Okay. Okay, there's one more problem here. The model indicates that a crop yield of 4,900 kilograms per hectare was achieved in what year? Round your answer to the nearest year. Okay, first of all, I want you to look at the graph. Okay, where is 4,900? Well, it's under 5,000. right? It's probably about right here. So as I go over, keep in mind, this is going to be right near 1983, right? We just did one like this. Our answer is going to be just about 1983. Because here's 4,900. So that's what we expect. What we're doing now is, now we have the value for y, the number of crops per year. We need to find out the year, so we need to find x based on y. So we're going to use our original equation, but now this time we're going to substitute 4,900 not for x, but for y. And we're going to solve for x, which is our year, 4,900. Now remember, the year that we predicted, that was 4,623, so it's a little more than 1983. 4,900 is 81x minus 156,000. If you truly want to solve, add 156,000 to both sides, and I think that gives you 160,900 equals 81x. I don't know if this will be an exact answer. Let's find out right now. No. So this is what it becomes. 1986.419753. Now I'm curious if you know what that means. First of all, this means years since 0 AD, right? That many years. But what this also means, so this means the year that it happens. But is this the year that it happens? This model indicates that a crop yield of 4,900 kilograms per hectare was achieved in what year? Round your answer to the nearest year. No, okay, so they ask us to round. So this actually goes against what I wanted to say. So I guess the answer they want is in year 1986. By the way, I was born in the year 1988. My sister was born in 1986. I wanted to say 1987, and here's why. Well, actually, you know what? 1986 would have been fine as well. Because in the year 1986, this was achieved. Okay? By year 1987, by January 1st, 1987, we have achieved it. But by January 1st, 1986, did we achieve it? No, we achieved it about 42% through the year, probably in the beginning of the month of June, right? Something like that. And by January 1st, 1987, we did it. So, one answer or the other would be better. In this case, when they say round to the nearest year, hey, let's do what they say, year 1986. So it's close to 1983. It's a little bit later than that. And there's your answer. Okay, we're going to do one more of these, but a different kind of problem. Here we go. This is the very last problem, and after that, I promise I'm done. Okay, by examining past tournaments, it is possible to calculate the probability that a school wins their first game in the National College Basketball Tournament. So, the number one ranked team wins their first game 97% of the time. This is kind of things they have. Third ranked team wins 87% of the time, and this keeps going down, and so on and so forth. So this is examining past tournaments. This is probably an average of what they expect through this, and this is kind of a nice. I like this problem. It's a really cool problem, especially if it's true. With this stuff, and you can tell that the lower ranked teams probably lose more often, and it's not necessarily just because they're worse. They're playing better teams. The first ranked team in a college basketball tournament probably playing ranked 16th or 64th or whatever it is, right? They're playing lower ranked teams. So it's expected more often that the upside teams, the ones that are seeded higher, were probably better to begin with. Now there are upsets that happen, but on average, this is what's happening. Now I'm talking about basketball. I'm sorry. And we are talking about the first game. So these numbers here are the ranks of the teams. So as the ranks go up, it technically go down, but as the rank value increases, the probability of winning the game decreases, right? So this is a negative correlation here, which isn't bad. It's just describing something different. As you're going to by lower ranked team, I mean a higher ranked team. Rank 1 is a good thing. As you go to ranked 1 team, higher winning percentage. Okay. Each school's rank going into the tournament is a strong indicator of their likelihood of winning the first game. This can be expressed as this equation right here, where x is their rank out of 16, and y is the percent chance they have winning the first game. So x and y, as we knew a little bit, and they define the variables. Very nice of them. Thank you. Okay, what is the slope of the line-intercept? What does the y-intercept represent? Blah, blah, blah. Interpolation, extrapolation, based on the model, something else. So, slope and y-intercept, I feel like I need to explain one more time, especially because they become a little unrealistic with regard to what we're talking about, all depending on what there is. So, actually, the slope one's not bad. all right, first of all, slope itself, negative 6.71. That is negative 6.71 over 1. This is rise over run. In this case, it's a fall over run. Negative 6.71 is regard to the drop in probability of winning. So this is a percentage value. 1, this run represents the rank increase. Well, I guess decrease, right? So when I say increase, when the number increases, that is a worse thing. If you are ranked second versus ranked first, you are in a lower place than before. So let me call it a rank decrease for that. So, which kind of goes opposite, right? Because it's positive. So what does the slope of the line represent? It represents that as you lower in rank, every rank you lower estimates. Now this is actually a cool value. This actually makes some sense. Every rank you lower estimates a 6.71% drop in probability of winning first game. So what that means is, because they don't have it here, and well, actually, which one do they ask me for? Ranked number 6. Well, okay, they don't have ranked number 2. Okay, ranked number 2 is expected to be 6.71% less than ranked number 1, 97%, or than what we predict to be ranked number 1, not just what's probability. So 6.71% drop from there, it's going to be around 91%, 90%. Not bad, right? And that's in between in this sense right here. And as I said, these points are not right on this line. This is a prediction line. We're doing it to do the best estimates we possibly can. And this probably has a very strong correlation, which means this line is probably a very strong fit for this data. Okay. Now, what does the y-intercept represent? Okay, well, this one kind of is strange because there is no rank 0 in anything. While in the years and crop thing, there is such thing as 0 AD. There's no such thing as rank 0 here. So this isn't the top ranked team. This is above the top ranked team. The 0th ranked team has a 106% chance of winning. Why did I say 106? Because that's this y-intercept. Has a 106% chance of winning their first game. Winning first game. So you see, the y-intercept, it's stupid because it makes no realistic sense with anything. But they did ask us to interpret the y-intercept, and that's exactly what it is. When x equals 0, y equals, when it shoots up here, 106. Hey, you know what? I answered the question. But what if we said the y-intercept was 1, just to be a little fairer for stuff? We expect the first ranked team to have whatever 106 minus 6.71% is. 99.29%. I know this is the actual probability based on the stuff, but the predicted probability based on a line would be 99.29%. So either or, I still explained what was there. Now, the 106 is not, and look, they're not asking us to predict the 0 ranked team. They ask us to explain it because we're going to use this 106 and talk about, all right, what about the first ranked team, second ranked team, whatever. Furthermore, there is a ranked team that eventually with this percentage will become negative on the other end. Where will it be? Probably around ranked 16th team or something like that, right? Eventually you plug in X so many times, this number is going to be more, it's going to be more than negative 106. And it's going to dominate this number and you'll get a negative value. Again, unrealistic. Eventually this thing goes through the line and then we have to cut that off. So these lines are not always perfect for what it is we're talking about. But let's do an interpolation, an extrapolation, which is really close to that 16th that I was talking about. And then we're going to look at one with the probability and figure out what ranked team that probably was closest to. Interpolation, according to the model, a school ranked number 6 has what probability of winning their first game? So a school ranked number 6, here's number 6. It's going to be somewhere swimming between 60 and 70%. Let's figure out what that exact number is. How? Use our equation, negative 6.71x plus 106. Substitute 6 for x, and we will find out what our y is. Because x represents the ranking. This is 6th ranking. Y represents the percentage. Let's figure out what that becomes. Negative 6.71. Oh, sorry, one second. Negative 6.71 times 6 is negative 40.26. So we're going to subtract 40.26 from 106. And that is 65.74. So what does that mean? Probability. Hang on. Let me write it over here. 65.74% probability. Ooh, what happened to my mouse thing right here? 65.74% probability of winning their first game if you're ranked 6th. That's still more than 50%. So it's not like, this isn't like school grades where this is like a D or an F. Okay? It's not like, oh man, that's bad. No, it's you have a higher chance of winning than not. So, as long as you're above 50%. So that's still good. At some point, they should ask the 50% one. I wonder if they do. The 52% chance. So, okay, so that's for ranked 6 team. This is prob of winning first game. Okay. Using this model, school ranked number 15 has what probability of winning their first game? Round your answer. Ooh, they said round your answer to the nearest percent. This would have been 66%, by the way, guys. Round to the nearest percent. Sorry about that. Round this answer to the nearest percent. Okay, let's do that. Ranked 15th, check this out. This is where I was talking about extrapolation. Outside the data set, 11, 12, 13, 14, 15. It's going to be somewhere down here following this trend line. It's going to be somewhere really close to 0%, right? We're predicting a ranked 15th team has a very, very, very low chance. How low? Let's substitute 15 in for X. Plus 106. Because remember, every team, every subsequent team after the one you're referring to has a 6.71% chance less probability of winning their first game than the one before them. That's what's predicted. So, negative 6.71 times 15. Ooh, negative 100.65. What does that mean? When you add 106 to that number, when you subtract that from 106, you're going to get 5.35%, which is rounded to the nearest whole number. That's about 5%. You expect a ranked 15 team. So I assume for this college tournament, they're talking about their 16 teams, right? Not 64 like I first said. A ranked 15 team has a 5% chance or probability of winning first game based on our predictions. Okay. That probably means they're playing the second place ranked team, which means they're probably around 95%. But remember, this line does not do perfectly from one to the next. It's just doing a line that's predicted based on these points. Not a very bad line, all told. This thing looks to be pretty accurate with regard to this. And this is probably how it really is, right? A ranked 15th team compared to a ranked number 2 team in basketball. Look, in baseball, the ball can fall wherever it does, and pitchers, some people catch it and stuff like that. In basketball, some teams have significantly more talent and they move the floor better. Check out the Warriors and how much they dominate so often. In football and stuff too, how they dominate. Baseball is a different story. Based on this model, a school with a 52% chance of winning their first game would have what rank? Round your answer to the nearest whole number. This is the very last question of every single problem we do here, so be relieved. We're almost done. Now what we're looking at is the Y value. The Y value of 52% is about right there. Okay. Now what number is that as far as ranking? Looks like we're going to be around the answer of ranked 8 team. That's what I'm guessing the answer is going to be just about at, right? So the other way of asking this question, and this kind of makes some sense here. If there are really 16 teams, and if 1 plays 16, 2 plays 15, etc., ranked 8 team plays ranked 9th team. These are the 2 closest ones that have almost equal chance of beating each other, right? These are the 2 closest ones. So it would make sense if the answer was 8 because they would have just more than 50% chance of beating this team right here, which would have just under 50% chance of beating them, right? Which is, we had 9 as 45%. So that makes sense with respect to this problem here. So let's go and see if it's going to be 8. Let's go and do what we're supposed to do. Substitute 52 for Y. Find out what X is. Subtract 106 if you like. Actually, I'm going to add 6.71x to this side. I'm going to subtract 52. So 106 minus 52 is 54. Divide by 6.71. 54 divided by 6.71 gives you 8.04. I'm going to write the whole thing. 7, 6, 9, 0, 0, 1, 5. So as this is more of a sequence problem than an actual function problem because it shouldn't truly be continuous, this thing rounded to the nearest whole number, the 8th ranked team. Okay. Because your only rankings can be 1, 2, 3, etc. So I think this would have been a much better sequence problem instead of whatever else. The line is just there to be a line, but the points on these integer things were much more important, like this one, this one, this one, etc. Not the continuous line, because there is no 6.5th ranked team. Right? Anyway, that's it. We're done. I know that was a lot of problems, a lot of explanation. Very near the 3-hour mark, in fact. I hope this stuff was really good for you, though. Looking all back, all the different problem types that we did, okay? Here are the things I promised I'd do, and I did. I did. Quadrilaterals, like I said, or quadratics, we're not really, I'm thinking geometry. I got to do a video for that. Quadratics, we're not really on here. Sorry. But they are on another video. In fact, if you do want to find that video now, I'm going to say click here. When you click here, I'll bring you to the video of the other algebra packet that you had where we had solutions for that stuff. Whew. 10:04 p.m. on a Friday night. Let's retire now. All right? Good job on this last problem here. Looking at this one more time. One other thing I wanted to talk about once again was the negative correlation. As I mentioned, as the ranks went up, technically as they went down, but as the numbers went up, the percentages went down. That's okay. Things happen with that. And eventually it has kind of a good domain and range that you got to stop looking at. Really from 1 to 16. Look, 0 didn't work either. 106%. We talked about how that worked, but that's it. All right. Fiend.